Good morning. It is Tuesday, June 8th, 2021. So welcome to day 2 of summer school. We have a busy schedule. We're always going to have a busy schedule. Today we are going to talk about our first major physiological process and talking about homeostasis. And then as we talked about, we have to build that foundation so we can spend all our fun time in organs and organ systems. And so we're going to start that by talking about the first level of our hierarchy, and that is going to be chemistry. Before we get to all of that, the last thing we need to do for the introduction is get a chance to talk more about the Mastering A&P and the resources that are on there. It is one of the 3 main things you have to purchase for this class, and there's a tremendous amount of information resources in there that is going to be valuable for you, invaluable really, for your completion of this class. As you can see, we still have a ton of stuff going on. Your unit review, your first one is due Thursday. Again, as I mentioned, if you have not purchased or if you have not received your lab manual yet, I am willing to be flexible with that. I understand that there's a back order on those. So as long as those are completed and turned in before the first exam by the end of next week, that should be fine. That gives you 2 weeks to get it, which should be enough time in an 8-week class. But after that, they will be due on time. But so the first one of those is due. Your Mastering A&P introduction, which we'll talk about more today, is due on Thursday. Your first Labster, which we talked about briefly, but I want to go over a little bit more, is there as well. And then your student info sheets, although most of you have turned them in and I've commented on them, and I will talk about that in a minute. Unit 3 review is due Friday. Your second Labster is due. And as I mentioned on Friday, we will do a practice lab exam because your first exam is going to be Monday, the 21st. And so this will give you 10 days, give you a chance to gauge how your studying has been going in this first week. And then from there, we can talk about what you need to do to be successful and get the experience of what that lab exam is going to be like. Next week, Monday, Unit 4 review, another Labster, and your first Physiox, which is another lab simulator that we'll take a look at as well. So that is the game plan. Like I said, it stays busy. Welcome to summer school. All right, questions on any of that? All right, excellent. So let us start where we left off with our review before we get into the lecture and everything that goes along with that. I want to talk about this Mastering A&P. So again, from our course home, from your course home, which looks slightly different from mine, you go to the My Lab and Mastering. And again, this is what mine as the instructor looks like. Your home page will look slightly different. But as you can see, there are these resources over here, and the 2 primary ones you're going to use is the e-text and the study area. I am a book person myself, but I do really enjoy the e-text for this. It is a very, very powerful e-text. It has a lot of really great resources. You have the ability to highlight components of this and be able to highlight them. You can make notes for the book and things along those lines as well. You can see your previous ones. It is a static textbook. So basically what that means is if you use it this semester and you highlight and you put bookmarks and you put notes in it, and then you come back next semester in a different class, it'll still be there. All of your notes, all of your resources, all of those things that you add to it will still be there. And the thing that I like about it the best is the search content. So if, for instance, as you can see here, I've highlighted some stuff myself. I put some notes in here. And then if you do a search, for instance, if you were interested, you can see my search was for mitosis. It gives you the definition. It gives you some information about it. And it gives you all the locations in the textbook where you have that, plus any of the virtual resources. So for instance, it actually links to our A&P Flicks, where it shows you a video on the process of mitosis. And these A&P Flicks are really amazing as well. So as far as e-texts go, it is a very useful one. One of the other nice things about this e-text is you can actually download chapters to your smart smart device, so your phone or your iPad. So if you're going camping over the weekend and aren't going to have internet access, you can actually download the chapter that you want to study, highlight it, make the notes, and then when you get back home, it'll sync it back to the interwebs, and you'll be able to maintain that information there. So it's really, really useful tool. If you like electronic textbooks, it's a pretty good one. However, where you'll be spending most of your time, my guess would be here in the, let's see, put that there, in the study area. The study area has all of the main resources, including your Physiox. Physiox is another lab simulator, and this Physiox will have activities that you will be turning in for grades. So let's go ahead and take a look at that first. When I click on the Physiox and I go to the exercises, here you see the list of all of the exercises that are here. I believe, what was it, Tuesday the 15th is when your Physiox exercise 1 is due. And notice as you look at this, you can see that exercise 1 has 5 different activities. Each of these activities is its own independent activity that you are going to do and complete, produce a lab report for, and turn them in. So at the end of this exercise, you will have 5 lab reports. I'm not going to bother spelling out lab reports because it's too hard. So each one of these is an independent activity. The way this works is you click on the individual activity. It gives you an introduction, what your objectives are. There are videos and things that you can watch talking about the equipment. There's a pre-lab that you'll take, and you can check your answers. And hey, look at that, just checking it blindly. Oh, messed up that one. Oh, messed up that one. All right, so notice I've taken that, good or bad, I don't care. I just want you to do the activity. Again, the point of this is to be learning it. But notice now that I've finished my pre-lab quiz, I have the choice of continuing, canceling, or most importantly, submitting. And what you're gonna wanna do is submit. Because what this does is this submits it automatically to the lab report. So I submit that to the lab report, and then it takes me to the next activity. You walk through, it tells you exactly what to do. I'm going to grab my 20 molecular weight cutoff membrane and put it in there. Once I do that, then, whoops, did I not do that? I did that. Oh, next is down there. Perfect. Excellent. Then I'm going to produce 9 millimolar of sodium chloride and dispense it onto the one side, and so on and so forth, and you'll go through all of the activities. Again, the point of this is to be a lab simulator. So you're gonna go through all of these activities. I'm gonna jump ahead. Once you are done with that, again, it's warning me, there is a post quiz. You can go back and look at your results to do that. Once you are done with your post quiz, you'll submit that, you'll submit all your data, and then there are these review sheets where you're gonna write answers to all of your these questions based on the information. And again, notice you can always go back and see your data while you're doing all of these and submit that as well. Notice when you're done submitting, you have your lab report. Now my lab report is not very impressive because, well, I didn't do anything. But all of your data, all of your graphs, all of those things will be here. And this lab report is what you're going to be responsible for turning in. So now notice the easiest way to do this is to scroll down to the bottom of your lab report. And notice at the bottom of the lab report, it says printable, savable version. Put your information in there. And then you have this print save as button. Most computers nowadays have a save as PDF option to them. So you can save this as a PDF, and that's what you're going to want to do. You're going to want to save this as a PDF to your computer. I'll just make sure it's on the desktop. Physiox exercise 1, activity 1, perfect. So there it is. I have saved that there and completed that activity. Now I can go back to, oops, hold on. So now I go back to our Canvas site under the modules in section 1. And notice down here in my lab simulators is my Physiox exercise 1. I'll click on that. Reminds me there are 5 different reports, 5 different lab reports, all of these things. I'm going to go to the assignment, and here I can now upload from the desktop that Physiox exercise 1, and I can submit that first activity. Of course, I'm going to need to, oh, look at that. It's all excited for me. I'm going to have to do that 4 more times with the 4 different activities. And again, I'll just come and it says, I know it says new attempt, but it does not erase the previous stuff. So if you want to do them all at once and submit them all at once, you can do that. If you want to do them 1 a day, you can do it that way. But again, I know it says new attempt, but it's not going to delete the stuff you put there before. So you can submit it all at once or submit them 1 at a time. I don't care how you do that way. So that is going to be something that is going to be the easiest way to submit that assignment. Make sure you just save it as a PDF, and you'll be able to do that without any problem at all. All right. Questions on that?
Nada.
Excellent. All right, so that is the Physiox. There are graded assignments there, but there are other resources in this study area as well. So let me close some of these windows. We can get rid of that now. We can get rid of this now. Go back to our home. That is something that you have to do and turn in for a grade, but there are a lot of other really great resources that are on here as well. You can look at individual resources by going through them this way, although often one of the easiest ways to see all of the resources that are available for you is to study by chapter. Now, our introductory chapters aren't terribly interesting, so let's go to something a little bit more fun, like, for instance, the muscular system. When we go to the muscular system, it shows you the portions of the e-text that are available, but it also shows you all the other resources, like, for instance, A&P Flicks. A&P Flicks are high-resolution animations of some of the materials you're going to be responsible for. So when we
nerve impulses, also known as action potentials, travel from the brain or spinal cord to trigger the contraction of skeletal muscles. An action potential propagates down a motor neuron to a skeletal muscle fiber. The site where a motor neuron excites a skeletal muscle fiber is called the neuromuscular junction. This junction is a chemical synapse consisting of the between the axon terminals of a motor neuron and the motor end plate of the skeletal muscle fiber.
So as you can see, they've got these great animations, do a really great job for those of you who are visual or auditory learners. It does a really nice job of showing these resources for you and helping you to be successful. Many of the more complicated physiological processes are described in a section called the interactive physiology, and let's actually go to that. Here you can see, again, there's not a whole lot for the early sections, but when we get to the muscles, when we get to the nervous system, and when we get to 431, the second semester, you can see that there are a ton of these that are going to be incredibly useful in helping you. These are interactive tutorials that help you to understand and master the material. And like I said, not a ton for the first part of this class, but when we get to the muscular system, there's a lot of stuff here that is really, really useful for some of these more complicated physiological processes. Before we get to that, though, we got to get through the bones. And one of the best ways to learn the bones is to take advantage of this practice anatomy lab. This practice anatomy lab is a virtual cadaver, for starters. So we have the human cadaver here, where, for instance, if we were interested in looking at muscles of the trunk, we can see this. We can highlight the individual muscles and look at them that way. It is something that is very, very useful. We can also, for instance, again, this is much more useful when in the classroom, but when we're in the classroom learning about the muscular system, we have models. And the models that we use are actually almost identical to the ones they have here. So again, they have all these models, all these images that show this information. You can use this for testing yourself. You can show the labels, you can turn the labels off. When you're feeling somewhat comfortable with this information, then you can start quizzing yourself, where it will show you a muscle like this and you get to try to guess. Oh, I got it wrong. What it is, and go through it that way. And when you're feeling particularly frisky, you can actually take a lab practical where it will show you a muscle and you actually have to write in the answer for that. So this is a great tool for studying the muscles. This is a great tool for studying the bones, which we're going to be doing next. So for instance, when we get to the bones and we're learning the skull, being able to identify and go through these things is something that is going to be very, very helpful. There is no homework assignment related with this practice anatomy lab, but it is a great, great resource. We'll use it for the bones. Notice also there is a fair amount of histology, not quite as nice as our histology histology atlas. But if you haven't purchased or gotten your histology atlas yet, this is not a bad place to start for looking at the different tissues that you're going to be studying and doing things that way as well. So again, no assignments in this practice anatomy lab, but it is a very, very useful resource. Also, notice this has a flashcard maker. For this practice anatomy lab, you can actually select what you want: cadavers, models, histology. They also have a fetal pig and cat dissection, which we won't be using, better in here. But you can actually make virtual flashcards that you can actually then download to your phone, so that you have the opportunity through the Pearson app to be able to, when you're on the go, study the muscles or study the bones. And you can totally, completely customize these flashcards to the precise bits of information that you are interested in. And there's all sorts of other things. Like I said, the easiest thing to do is usually just go to the chapter. And when you're on that chapter, it shows you all of the individual resources that are available for it. So it's a great, great tool. It's something I strongly recommend. Again, there's flashcard makers and all sorts of other great things that are here to help you to be successful. As I mentioned, to encourage you to get on here and use this, there is, and I'm not sure how I get to my assignments. There is an introductory assignment. This introductory assignment is a 4-point assignment and basically just familiarizes you with the adaptive learning process for the resources that are on here. So that is something that you can work on while you're here as well. All right. Yes, was there a question?
Yeah, I had a couple questions. Is it possible?
I'm sorry, you broke up in the middle there. You said, is it possible? And I didn't catch the rest of that.
Is it possible to put images on those virtual flashcards?
Yes. So it does. Yes, I believe it is possible to do images on that. So.
And for the Physiox, the lab assignments.
Yes.
Would we have multiple attempts like the Labsters, or?
Yeah, absolutely. Yeah. So and that's another thing too. Yes, you do have multiple attempts through it. However, again, I see this as a learning process. So if you only get 50% correct on that pre-quiz, I'm not going to penalize you for that. Again, this is another example where I'm looking for time and effort. As long as you're completing the activities, you are not going to lose points on this one. This one doesn't do points the same way that the Labster does. So this one, I'm looking for time and effort. I'm looking to see that you've completed the activities, you've done all the experiments, you've collected all the data, you've thought about the information, but you're not going to lose points for getting things wrong. Now, that being said, if you want to do it multiple times, you're absolutely capable of doing it multiple times. But as long as you're putting time and effort into it, you will get the full points. The Labster is directly integrated into Canvas. And so that's how why the scores go in the way that they do for that. Now, you won't have to submit the Labster. It's going to submit it automatically when you take that, whereas this is something you actually have to submit it. So actually, that's a great point. Let's go back. So notice if we go back to our modules, So notice for the Physiox that I have here in section 1, it's just a place to drop the materials off. However, when you're, for instance, if you haven't done so already, if you're doing the Labster, when you click on the Labster link, it actually takes you directly to and loads that Labster up. You do the activity from here. It is also a lab simulator, just like the previous one. It takes a little time for it to upload and everything that goes along with that. But when you complete this activity, there isn't going to be anything that you're going to need to submit. It submits it automatically to Canvas because it's already integrated within Canvas. Whereas the Physiox, you actually have to have the lab report and drop it in because it's not synced with Canvas the same way.
So we are responsible for both labs, Physiox and Labster.
Yeah, both Labster and Physiox are lab simulators that you're going to be doing. And as I said, your first Labster is actually due Thursday. So that's this one here, the homeostasis one. So notice here with homeostatic control, it's slowly loading. But when you complete this, it will automatically submit it to Canvas, and then you can actually view your score in the dashboard for that. So here we get a chance to.
Welcome to the homeostasis simulation. Here you will learn how your body regulates many physiological variables to maintain a healthy equilibrium following external stimuli. Click continue to start with your mission.
So for
This simulation uses voiceovers. If you don't have audio, click the speaker symbol in the top right corner of your lab pad to switch the player. If you disable the sound effects, the lab pad will pop up whenever there are instructions to read. Select the audio setup you prefer. To mute individual audio options, simply select them. Click continue to learn how to navigate through your mission.
So again, as you can see, she's a bit chatty, but it walks you through and you go through all of the activities on this, and this is going to submit it automatically. When this is done, when you are done with that, when you go back to your, actually, I think for this one, I think I need to go here. That one. When you are on your, when we're in our Canvas site, when you go to your Labster dashboard, after you've completed one of the Labsters, then you will see your score here. This Labster dashboard is not where you go to do the activities. It's where it shows you the scores for your activities. So the place you go to do the activities is actually in the modules. So when you go to the modules, under the lab simulators, you can see for this section, we have the homeostatic Labster, mitosis Labster, cell membrane, and transport Labster. And then we have a Physiox, and then there's one biointeractive activity from your textbook that we're doing as well. So these are all the lab simulators. The Labsters are all integrated, and so, but you go here to do the Labsters, and the Physiox, this is where you'll go to submit it. All right. I think that is everything else that we didn't get a chance to look at last time. I know I've thrown a lot of information at you, but again, remember this is recorded and you have that opportunity. But any questions on any of this that we have covered here as far as the rest of the resources you're available for, responsible for in class?
Question: when are the recorded here going to be uploaded?
So as I mentioned, it usually takes, so it varies in time. I have submitted our first lecture already to YouTube. I don't know if it has populated yet, but basically there are four things that delay the presentation of the lectures onto YouTube. The first is once we're done with the lecture for the day, Zoom has to compile the lecture. And again, with these being 4-hour lectures, that takes a bit of time. It usually takes a couple hours for that to occur at least. And that's when my computer's on. If I walk away, if I'm not doing other work on the computer and my computer goes to sleep, then it stops compiling. So it can take hours for that to happen. Then it takes time for me to upload it to YouTube. Again, that usually doesn't take nearly as long, a couple minutes for it to upload, 5 minutes for it to upload to YouTube. But then once YouTube gets it, it takes time for them to process it. And their processing time, I have found, varies dramatically. Sometimes it is processed within 5 minutes. Sometimes it takes 3 hours for them to process it. So I don't know what that is. Maybe it has to do with how many people are uploading things to YouTube or whatever. But my goal is usually to try to get it up by the next day. However, again, with us having an 8 o'clock in the morning class, that means that the previous, and us having back-to-back days, because usually that's not an issue, right? During the normal semester, we have a Monday class and we have a Wednesday class. So if it doesn't get up till Tuesday, that's not that big of a deal. But in some cases, it may be possible that the previous lecture won't be posted before the next before we have the next lecture. So again, I'm not purposely trying to delay it to penalize you for not being there or anything. It's just that this is how this is the process. So I try to get it up onto the YouTube as quickly as I can, but there are delays. But like I said, I have submitted yesterday's lecture. I haven't looked to see if it is available yet though. All right. Any other questions?
I got a question.
Yes.
I was wondering if you could possibly show me, I'm going to share like a Unit 1 review towards the end of the chapter. It's the stuff towards the end of the chapter that we're doing, right?
Oh, on the lab manual?
Yeah, in the lab manual.
Okay, yeah, sure.
Or if you can walk through that.
Yeah. So here, let's do this first. So again, the easy thing to remember is I will always, when we have the unit reviews due, I will always put the page numbers so you know which page numbers to expect for that, okay? However, in each section, when you get to the reviews, so let's go ahead and make the screen big now. When you get to the reviews, you can see that it says unit review. And the key to the reviews is that for all the reviews except for Unit 3, there are two parts to it. The first part is a check your recall. The check your recall is more where you're regurgitating information, right? Doing labeling, doing processes, doing things along those lines. And those are usually a couple pages. And then the second part is a check your understanding. The check your understanding is more critical thinking, comparative types of questions where you're kind of using the information you have to extrapolate other pieces of information from there. So again, I really like that it has both of those components to it. And so both of those parts are going to be due. And again, those are encompassed within those page numbers. Like I said, the only one that's different from that, and I guess since we're looking at it, let's go ahead and look at that. And again, I don't know why they did this. It angers me, but doesn't really anger me. I don't really care. For Unit 3, and I'm guessing it's because it's the microscope part, what they did in Unit 3 is rather than putting the review questions at the end, they've put the review questions at the top of the page and then all the exercises underneath it. So this entire unit is basically pages 62 through 68, or 63 through 68. There are 10 check your recall questions at the top, and those are what you're responsible for turning in. But all the rest of them, it's going to be a separate unit at the end of each unit of the lab manual. Okay? Does that make sense?
Yeah, it did. Thanks.
Excellent. All righty. Excellent, excellent, excellent. Any other questions? All right, so before we dive back into lecture, there are just two more administrative type things that I want to talk about. I have just started grading your syllabus and proctorio quizzes, and there are a couple quick notes that I wanted to make about that as we go through them. First is, again, about the scanning of your area. One of the most important things that you can do to maintain the integrity of this class and to ensure that you are successfully able to complete this is to show me your workspace. Your job is to take your computer or take your camera if it's independent. I'll go ahead and disconnect mine here so that we can do this. And you have to show me your working environment. Many of you, not many, some of you, while you're spinning around, stay in the middle of the screen. That doesn't help me. What I want to see is the working space around you. So you need to show me your workspace, show me the space around you. Now, obviously I have a lot of junk around my space, so that's not necessarily what I want, but you have to show me your table, show me the wall behind you. Like I said, so that you don't, I know you don't have a wall of papers. I know this is not, let me plug back in my microphone too. No, this is not the most intuitive way to take an exam. We're not used to being hyper observed during this. We're used to being able to scratch our head. We're used to being able to look off into space and do things like that. But that's not something that is as easy to monitor on something like this. So the better you can be about slowly showing me your space around you makes me more confident that when you're staring up and to the left while you're taking the exam, I can think, okay, they've shown me that there's nothing up there. So and they're just thinking about what the question is, or, you know, they're not looking down at a piece of paper, they're just scratching their head because it itches. So the more you can show me the area around you, the more comfortable I can be that you're maintaining the integrity of the exam. It is very important to do that. If you don't do it properly, then you will lose at least 10% on your exam. And if it's severe, you could get a 0. So it is important to do. I know it's not something we're used to having to deal with, but welcome to online formats. Lighting is important. And again, especially with these cameras, when you're backlit, and again, Terrence, I hate to use you as an example, but since I see you right now on the corner of my screen, you've got that beautiful view behind you with that amazing window. And because of that, I cannot actually see your face at all right now. So you have to be really cognizant of your lighting in there. You do have an image of yourself on camera. And again, it's fine for now, I don't care. But on the exam, you have to be visible. So make sure you're visible, make sure you're not too backlit so that, that the camera can see you well. And again, you have an image of yourself to make sure you're there. Along those same lines, make sure you're in the center of the field of view. It doesn't do me any good if you're taking the exam and all I can see is the top of your head. Right, so make sure you're in the center, and again, you have an image of what's being recorded there, so you know what is going on that way. You are restricted from having a second monitor. It won't allow you to project to 2 monitors through the Proctorio, but if you have a second monitor on your desk, like I do, notice I happen to have a second monitor on my desk as well. If that is the case, then you need to take a towel or something and cover it, or flip it around or something like that, so that I know that you don't have a second computer hooked up to that second monitor, to make sure that it is off and that it is not being used. Yes, to answer your question, I haven't had a chance to check everybody's. I just started going through these, but what'll happen is once I get them graded, I'll submit them. And then if I have any questions or concerns, I will post those in the comments for that. So I will be able to directly communicate with people about those. And then also I'll be able to do that with the chemistry quizzes as well. Lastly, I think this is last. Is this last? No, 2 things. Okay. No earphones. I know some of you have your microphones connected to your earphones. Yeah, then you just leave them on the countertop so that the microphone can pick up the ambient noise. But you can't be wearing any kind of earphones or earbuds or anything like that. If you're wearing a hoodie, you have to show me your ears to show me that you're not wearing anything, so that I know you're not getting information or listening to the recorded lectures or anything along those lines. And then lastly, and I know this is the silly one, but every semester it happens. So I want to just nip that in the bud right now. When it says to show your ID, I've had students, and in fairness, there was also one instructor that I know who did this. There's that green box in the middle of the screen when you're supposed to show the ID. You do not hold your ID up to the green box. Right? I've had students who have done that. You put it on camera so that it lines up with that green box. So you're using your ID to line it up. So you're showing the ID to the camera, not holding it up to the green box on the screen. I know that seems silly, but like I said, I know of at least one instructor and several students who have done it that way. We're not quite at the point where the whole computer screen can view you, so you have to hold it up to the camera. All right. So again, all of you should have taken the chemistry quiz. Hopefully most of you, when was the Proctorio one due? Proctorio one due today too? Yes, it is. So you should have taken both of those already. Any questions on that from from your end? As I go through these, I'll make comments on them if I have any concerns or questions for you guys. But do you guys have any questions or concerns for me now that you've taken those 2 introductory Proctorio practice quizzes?
Professor, I'm sorry, could you repeat that information about the ID and the camera?
So one of the things that you have to do is verify that you are you on the exam. So at the beginning of the Proctorio quiz, it asks you to show your ID. When it does that, there is a green square or a green rectangle in the middle of the screen, right? Your job is to hold up your ID so that it lines up with that green rectangle. I have had students that take their ID and hold it up to the green rectangle on their screen. Notice I'm holding it up to the screen and you can't see it because it's not on camera. And like I said, it's okay if you've done that. I know of at least one instructor who did that, but to avoid some of the questions, you have to hold it up to the screen, to the camera, so that it lines up with the screen. So that's what I was saying. I don't think, again, I haven't looked at all of them, so I've only looked at 4 or 5 so far, but the ones that I've looked at, nobody did that. Everybody did it properly. So, but like I said, I know it's been an issue in the past, so that's why I mentioned it now. All
I
right.
have a question.
Yes.
For the quizzes, do we ever get to see the right answers or go over them?
Excellent question. So what will happen with the real exams? So with the real exams, what will happen is after we take the exams, after I grade them and curve them, then I will make the exams available for you so that you'll have the opportunity to go back and review the questions and review the answers and see your points on those for that, usually for about 24 hours. And then I close that down again. If you want, if you have questions or you want to see it again, you can always come to my office hours and I can make it available for you that way to see it that way. So I do want it to be a learning process. So there will be an opportunity after each exam, after they're graded, for you to be able to see the results for that. Okay. Excellent. Any other questions? All right. Last thing that I wanted to do from an administrative standpoint is, again, I have not had a chance to view everybody's student info sheets that have turned, but I've seen most of the ones that have turned in. And there are a couple comments that I wanted to make about them. Some of the simple things first, again, a lot of nursing students, not a surprise in a class with like this, but there was a lot of diversity of what other people were interested in doing in this, as well as including a tech program, whatever that is. I'm not sure what that is. You guys were pretty open to everything when it came to what you're interested in, wanting to know everything, although a fair number of people were interested in things like the bones or the cardiovascular system. I had someone who was interested in fingerprints, which I think is really cool. That was a new one. And one of you sick puppies out there was interested in histology, which I love, because again, it's one of those things that you're absolutely going to hate until you get comfortable with it, and then you love histology. So that is very, very cool. A couple things that I wanted to talk about and addressed were the studying techniques. One of the things we kind of talked about in the last class is that you can pretty much use any textbook you want, because for the most part, the textbook material is the textbook material is the textbook material. Now, I do tend to try to lecture to our textbook, and the reason for that is that I think that from a learning standpoint, having me present information in a way that is similar to the textbook can sometimes make it easier for you to be able to comprehend the information when you hear it in a different voice. So for instance, I may describe a process in 6 steps because our textbook describes it in 6 steps, but a different textbook may describe it in 7 steps. Now, when it comes to the exam, are you going to lose points if you use 7 steps instead of 6 steps to describe it? No, Dahlia's right, shaking her head. No, absolutely not. You can describe it in 14 steps for all I care. I don't care how many steps you use to describe it as long as all the information is there. What I care about is the information, right? So again, sometimes it can be confusing if I describe something in 6 steps and the book describes it in 8, but it's not about the steps, it's about the information. The other important thing to remember about your textbook is that your textbook is not a romance novel. It doesn't have to be read from cover to cover. There are some people who need or want to read the entire chapter because they need to see how all the pieces fit together for it to make sense to them. Other people are completely overwhelmed by reading the entire chapter. Right? Again, the information is the same, but how you're tested on it, what my expectations for you on it are would differ from teacher to teacher. I see my job as a teacher to be a tour guide, right? Weekend's coming up. So of course, one of the things you might want to do is fly to France for the weekend. And when you're sitting there in Paris, do you start up in the upper left-hand corner of Paris and go street by street down through the entire city of Paris? Is that how you tour Paris, especially if you only have a weekend to do it? This is the part where
No.
you respond.
No.
Excellent. No, exactly. It's not an efficient way to do that. Instead, what you get is a tour guide. And that tour guide takes you to the 10 most important and interesting places. And that's my job. My job in this class is to focus the textbook, focus the material to the 10 most important things. There may be 20 concepts in a particular chapter, but now they're not all equally important. So I'm going to pull out the 10 most important ones, and that's what we're going to focus on in class. And the things that we talk about in class, the things that you do on homework assignments, the things that you do in your lab simulators, those are the things that are important. And the things that I think are important are the things that are going to be on the exam. If you do not have a homework assignment on a concept, we don't talk about it in class, right? There's no lab simulator responsible for it. Even though it's in your textbook, you're not responsible for it. You're not responsible for anything in the textbook that we don't cover in some format. Now, there is one caveat to that. Let's say, for instance, we get to the integumentary system on June 18th. And on June 18th, we're running behind because we almost certainly will be by that point in time. And so I may say to you, look, we don't have time in class to talk about burns, but burns to the skin are an important concept. So make sure you read that in the textbook because it is going to be on the exam. So if we run out of time right before the exam, I may do something like that where I'm not able to cover something, but I will explicitly tell you, go and read this because it's going to be on the exam. But if we don't have any homework assignments on burns, we don't talk about burns in class, we don't discuss it any other way, then burns isn't going to be on the exam. So it's again, you're not responsible for everything in the textbook. You're responsible for all the things that we talk about, all the assignments that we do. As I said, I don't have to be tricky. I'm not going to pull some random piece of information that you've never heard of or never thought of just because it was in the textbook. That's not the point of that. The point of this is to understand the important concepts. Now, the flip side of that is if I'm taking the 20 concepts in the textbook and distilling it down to the 10 most important, then you need to own those 10 important concepts. One of the things, and I'm sure if you've talked to anybody who's taken me as an instructor or looked at my reviews or whatever it is that I'm a stickler for details. The way you maximize your points in this class is by being specific and being descriptive. Right? Again, when I'm usually grading the exams by hand, I use 2.5 red pens on this first exam, writing describe, explain, be specific. I want details. Don't just tell me that sodium enters the cell. You're going to tell me that sodium enters the cell through a voltage-gated sodium channel that opened at the -60 millivolt threshold because it is trying to bring the cell to its equilibrium potential of +66 millivolts. I want details. All right. But again, that's what I'm giving you as well. So the outlines are a great starting point for it. Again, that's the material we're going to be covering, but you're responsible for it to the details that we want. Notice my slides are not my script. I'm not just sitting up here reading this. It's just an outline to remind me of the things we want to talk about, and you're responsible for that to the level of the information we talk about. A couple other people asked about extra credit. Again, I do not give extra credit assignments because what I find is someone bombs the first exam. They come to me asking for an extra credit assignment. I give them that extra credit assignment and they work on that extra credit assignment. And while they're working on that extra credit assignment, they're not preparing for the next exam. So when the next exam comes around, they bomb that one as well and need more extra credit and so on and so forth, right? There are extra credit opportunities, the 5 for 5s, which if you haven't done, you have a chance, one last chance to do those today. Are those, all right, I curve the exams, they're open lab. There are some extra credit opportunities, but all of the extra credit in this class is going to relate directly to doing stuff in the class. I don't give outside assignments because anytime you spend working on an outside assignment, you're not studying the actual material you're supposed to be studying. And again, your grade in this class is supposed to be based on your work and your effort, not on extra credit. This isn't an independent study course. All right. Couple more quick points. Some of you are retaking 430. I don't think anybody here, I'm trying to remember, I don't think there's anybody here who took me for 430 and is retaking it. So I think that's a good thing. But one of the things that I want to warn people about who are taking 430 is when you're retaking a class, sometimes there is a comfort with the material that can be a trap. When I'm talking about some concept in your mind, you're saying, oh yeah, I remember when they talked about this in my previous class. And there's a tendency to check out or not to pay attention to the information or not feel frightened about this class, which you should be. When you're frightened, you're motivated and you're going to be studying. If you're comfortable, you're not motivated and you're not going to study. And so all I would remind you is that the reason you're here is because you weren't successful. For whatever reason, you weren't successful the first time you took it. So try to keep it fresh. Try to come at it fresh. Try to not be too comfortable with the material so that you're motivated to study and to be successful. All right. Also, some of you insanely are taking other summer classes. Now, in fairness, nobody said what their other summer classes were. Hopefully it's something fun like racquetball or something along those lines. But again, the thing that I want to emphasize is this class requires a tremendous amount of time. 8 weeks is an unreasonable amount of time to learn this information. We are doing the first 5 chapters of the textbook in 2 weeks. Then you have 2 weeks to learn everything you ever wanted to know about bones, 2 weeks to learn everything you ever wanted to know about the muscles, and 2 weeks to learn everything you ever wanted to know about the nervous system. It is unreasonable and unfair. And the only way you're going to be successful is by basically using every free moment of time to prepare and study for this class. And if you're taking another class at the same time, that's going to be very, very challenging. So I want to strongly encourage people who are taking other classes to reconsider that, and so that they could really focus on getting the grades that they want. Again, most of you are nursing students, pre-nursing students trying to get into nursing programs. And there's a big difference in getting into a nursing program if you get an A in this class versus a B in this class. So think about that. I know many of you are taking summer school because you feel the pressure of time. I have to complete this by X date so that I can keep going and so on and so forth. But remember, it doesn't help you to rush through these classes if you don't get the grades that you want in them. All right. Excellent. All right. And then last and definitely least, a couple people were interested about my information. I have been teaching at American River College now for 15 years at American River College. I've been in the Los Rios district for 18. Prior to that, I was teaching at Davis and a couple other places as well, UC Davis. UC Davis is also where I did both my graduate and my undergraduate work. I have I have always been interested in science, love science. I got my PhD in neuroscience, actually studying the development of the visual system. After completing that, I had basically 2 choices. You can, when you get a PhD in neuroscience, you basically either are going and working in a lab for the rest of your life, or you're teaching. And while I loved working in the lab, doing experiments is like walking on the moon. It is the greatest thing ever. I was not interested in spending the rest of my life writing grants and chasing money. I tremendously enjoy teaching, especially for motivated students like you. Nobody takes this class just for fun. You know, notice when I looked at the reasons people were taking this class, nobody said fun, because this class is fun. People are here for a reason, and that tends to be motivated students. And so it's a very fun population to teach. All right. Questions on any of that? All righty, excellent. So that is the rest of our introduction. Again, more time than I wanted to spend on this today, but hopefully that answered any questions and got the rest of our stuff taken care of. Real quickly, if there's anybody who has not taken their attendance quiz yet, please do that. The access code is LOCK. Again, this is the way you show me that you are here. This is the way that you show me that you want to be in this class, that you are attending, and that you are going to stay enrolled in this class. So please, please take that. All righty. With all of that now finally in our pocket, we can move on to and back into our lecture, our introductory lecture. Now, as I mentioned, we are going to talk now today about our first major physiological process, and that is the concept of homeostasis. Homeostasis is a condition of equilibrium in the body's internal environment produced by the ceaseless interplay of all of the body's regulatory processes. right? Which is an awesome statement. And as I can see, many of you are furiously writing this down. And that's definitely important to do, because one of the things that you can do after class today is call grandma on the phone, and grandma say, hey, grandma, guess what? Homeostasis is a condition of equilibrium in the body's internal environment produced by the ceaseless interplay of all the body's regulatory processes. And she'll be super impressed, and she'll send you 20 bucks in the mail. However, it's a big, huge mouthful. And it would be convenient if we could distill this concept into something a little bit easier. And luckily we can do that. Homeostasis is actually a state of dynamic stability. Now, someone remind me, what does dynamic mean?
Like moving.
Excellent. And what does stability mean?
Balance.
Right. How about, or not moving, right? These are kind of counterintuitive processes. Dynamic is constantly changing and stable is not changing. So how can something be dynamically stable? Well, let's think about this. Give me an example of something that we maintain homeostasis of in our body.
Temperature.
Excellent. Body temp is a great example. If I were to take everybody's temperature in this class right now, what would everybody's temperature in this class be?
Around 98.5.
All right. But you said around. What do you mean by around? Is everybody going to actually be exactly precisely 98.5?
No.
No. And in fact, if we were just talking about you, Brian, and you took your temperature right now, is it going to be 98.5?
Guaranteed it wouldn't.
Probably not. Exactly. Right. But even if it was 98.5 right now, what if we took it a half an hour from now? Would it still be 98.5?
Probably not.
No, it might be 98.1. And if we took it an hour from now, it might be, 98.9. And then we take it a little bit after that, it might be 99 even. And we take a little after that, it might be 97.5. Notice it is constantly changing, right? Maybe you just finished having a bowl of hot soup. Maybe you just finished walking up 2 flights of stairs. Maybe you've been sitting still for an hour and a half in a chair, listening to me ramble on and on and on, right? Someone opens a window, someone turns on the air conditioning. There is constant changes. It is constantly adjusting to its environment. However, if I take Brian's temperature an hour from now, is it ever going to be 117?
Nope.
Or 42 and a half? No, absolutely not. While it is dynamic and it is constantly changing based on what's going on around him, it is dynamic within a very narrow range of values, a very stable range of values. So this dynamic stability means that it is constantly changing, but within a narrow range of function. So again, that temperature is never going to be 117. It's never going to be 63, but it can fluctuate dramatically within that narrow, stable range. So, and that's the job with homeostasis. Homeostasis is about keeping not just body temperature, but pH, water levels, calcium levels in our blood, glucose levels, so on and so forth, maintaining that dynamic stability, allowing us to adapt to our environment, but keeping us within a narrow functional range. And that's what homeostasis is. Homeostasis is about maintaining this dynamic stability. Now, we can't do this on our own. We need some way to monitor this. So what parts of our body, what organ systems that we have help us to maintain this homeostasis?
Is it the nervous system?
Yeah, nervous system. Nervous system is specialized for communication. That plays a huge role. But wasn't there another one that also was specialized for communication?
Endocrine.
There you go. Absolutely. So it is our nervous system and our endocrine system that is going to help us to maintain this homeostatic balance within our body. Now, to do this requires some work. It's all about maintaining this balance like we talked about. And so there are certain components that are necessary to be able to maintain this balance. Let's think about this. Obviously, the first thing that we have to have is we have to have some type of disturbance. There has to be some type of disturbance that upsets the balance of our body. So the first thing that happens is there's some type of disturbance. Once there is a disturbance, right, then what has to happen now? What's the first thing that happens once there's a disturbance?
Your body recognizes there's a disturbance, sends out the signals to
Okay, let's go
counterbalance.
back a second. Absolutely. We have to recognize that there is a disturbance. Usually this works the other way around. Usually we're all sitting in the classroom right now. And when we're sitting in the classroom right now, I say, what would happen if someone was breaking into your house right now? So let's flip it around, right? Here we are working together, learning material. And what happens if the fire alarm goes off at American River College right now? Is that going to change our behavior here in the classroom?
No,
Why not?
because we don't know what's going on.
Exactly, because none of us are on campus. And unless you live across the street, you're not hearing that alarm, and that's not doing anything. In fact, the whole time I've been talking, my wife has been sitting over here on a chair, and she's been furiously blowing on a dog whistle the whole time that we've been talking, right? Has it changed anybody's behavior?
Nope.
No, why
No.
not?
We're unaware.
Right, exactly, because you can't hear it. And quite frankly, she hasn't been doing it. But the point is, you've got absolutely the right idea, right? The first thing that has to happen is we have to have some type of receptor. And that receptor is able to receive or perceives the information, right? It receives the information that there is a disturbance. Right? And then also, as Brian said, it then has to send that information somewhere. And where it sends that information is to what we call the command center. The command center basically has three jobs. The command center's job is to receive the information, process that information, and then make a decision on the information. Right? Processing that information, make a decision based on that information. Once it makes that decision on that information, it then sends that information. It doesn't actually affect the change. It sends the information, and it sends that information to our fourth component. And that fourth component is what we call an effector. The effector, as the name indicates, is what affects the change to bring us back into balance. Now, let's go back. Where are our, or what are our command centers?
Brain.
Yeah, nervous system or
Endocrine.
excellent. So our nervous system, our endocrine system, those endocrine glands, those are the command center. Those are the ones that are either producing the hormones or producing the electrical signals that send them to the effectors. What are the things in our body that can be effectors?
Hormones.
Well, remember, the hormones are the signals that are being sent, but I do like where you're going with this. One of the things that can be an effector are glands, absolutely. So glands are things that can be effectors. What else can be effectors?
Muscles.
Muscles. Now, granted, we haven't talked about muscle tissue yet, but how many different flavors does muscle tissue come in? More than two.
Three.
Three. What are they?
Three. Skeletal, smooth, and cardiac.
There you go.
Yeah.
Perfect. So there you go. The effectors, the things that affect our change in our body are going to be skeletal muscle, smooth muscle, cardiac muscle, and glands. And their job is to bring us back into balance. This idea of homeostatic balance is something we are intimately aware of, right? And it doesn't even have to involve biology, right? Again, it's summer, so this isn't the best example, but we can make it work. If this was winter instead, and someone left their window open, which they could have quite frankly done this morning because it was freezing outside this morning, right? So you leave the window open and that cold air comes inside. That is our disturbance, changing the room temperature. So luckily we have receptors in our house, and those receptors in our house are the thermometer. They have a sensor that measures the temperature in the house. They send that information to the control center, which is our thermostat. The thermostat, right, knows that the temperature in the house should be 78 degrees. And it's receiving information from the thermometer that it's only 72. And so our thermostat processes that information, sees that they're not the same, and makes the decision that we need to bring the house back into balance. Of course, the thermostat can't bring the house back into balance, so instead it sends the signal to an effector, in this case your furnace, which turns on the hot gas, right, blows the hot air into the house, and brings the temperature back up. And does our bodies work the same way? Absolutely. You stepped out onto the front porch this morning to grab your newspaper, right, at 6 o'clock in this morning when it was about 62 degrees outside. And you stepped outside in your pajamas and the door locked behind you. And the problem is you don't wear pajamas. So there you are, naked on your front porch, 62 degrees outside, right? Do we have sensors in our skin that measure our body temperature? Absolutely. They send a signal to our brain, which processes that information, realizes our body temperature is dropping. So it sends a signal to our effector. And what would the effector be in this case?
Muscles.
Which kind? Remember, it comes in 3 flavors.
Smooth.
Well, what happens when you get cold?
Skeletal.
Yeah, skeletal. You shiver, right? Your skeletal muscles contract, and that helps to bring you back into balance, right? And so it works the exact same way. We have a disturbance, a sensor that measures it, a command center, a control center that processes that information and makes the decision, sends that information to an effector, and brings our body back into balance. All right. And it works the same way if we get hot. All right. By this afternoon, I don't know if it's going to be 100 degrees, but let's pretend it's going to be. And you're sitting outside, right? Instead, the effector is going to be your sweat glands, causing moisture to be produced that evaporates away and lowers our body temperature. So it's all about maintaining this balance. Now, it is a little more complicated than that, but not much, right? Especially now. We have these smart thermometers. Back in ancient times, and by ancient times, I mean in my days, you had to make a decision of whether you wanted the heater on or whether you wanted the air conditioner on. There was a little switch on your thermostat that you had to send back and forth so you could pick one or another. But now, thanks to things like Nest, you can have a smart thermometer where you can set a range, a stable range of values that you want your house temperature to be. And if it goes above that, the air seat goes on to bring it down. If it goes below that, the heater comes on to bring it up, right? And these smart thermostats are very sophisticated that way. My sister, when she was pregnant with her first child, her range of temperatures that she wanted the house at was 71 degrees. If the house got hotter than 71, she was sweating profusely. If it got lower than 71, she was shivering uncontrollably. So her house had to be 71 degrees exactly, right? Not a very wide range, but it's still a range. And the body works the exact same way. We get hot, we sweat to bring it down. We get cold, we shiver to bring it back up. Now, and again, another different way to look at it, but it's the exact same way. There's a disturbance, receptor perceives it, sends to the control center, sends the effector, brings the body back into balance. So you step outside, you get cold, your body starts to shiver. And then do you continue to shiver from now to the end of time?
No.
No, of course not. And the reason for that is because we're constantly monitoring this process with what we call a feedback loop. And how many feedback loops are there? Types. How many types of feedback loops?
Positive and negative.
Yeah, 2. Absolutely. A positive and a negative one. Absolutely. We have 2 types, positive and negative. One of them's got to be good, and the other one's got to be bad, right? Because one's positive and one's negative. Positive, as we know, is definitely good. Negative, we know, has got to be bad, right? Is that how that works?
No.
No. So what do I mean by positive and negative? Let's start with negative. What do we mean by a negative feedback process? Not a bad guess. Positive and negative also refer to charges. Absolutely. That is definitely one of the ways we'll use it in this class, and we'll use it a lot, but not in terms of the feedback. What do I mean when negative?
It's when something happened in the organism, which is not normal, like.
Okay, and so then what do we want to do when that's the case? I don't have a ruler. See, normally I'm in the classroom and I get to use the yardstick for this. I don't have anything like that. All right, we'll use my scissors. So,
when women go to labor.
Yeah, so we'll talk about that one in a second. Absolutely, great example. So, I want to balance these scissors on my hand. Now, if it starts to fall to the right, what do I need to do to maintain balance?
Push it back to the left.
Bring it back to the left. Absolutely. Basically, what I need to do is cancel the disturbance. Or if I wanted to be more sophisticated, I want to negate the disturbance. Most of our feedback processes in our body are negative feedback processes. We have a disturbance and we want to cancel or negate that. We just finished talking about a great example, temperature. My body temperature goes up. I want to sweat to cancel it and bring it down. My body temperature goes down. I want to cancel that and bring it back up, right? Or my pH of blood goes up. I want to bring it down. Or my glucose levels drop. I want to bring them up, right? We have a disturbance and we want to cancel that disturbance. And when we cancel that disturbance, we're able to bring it back into balance. A positive feedback mechanism, however, we enhance the disturbance. Now, if we try to go back to the example of me balancing this scissors on my hand, it doesn't seem to make sense if it starts to fall to the right that I'm going to bring it more to the right to bring it back into balance, unless I want to bring it all the way back around, right? But again, it's still kind of, my analogy still kind of falls away that way. But there are times where we actually want to enhance the disturbance, make it bigger, right? And to bring it back into balance. Can someone give me an example of this? I think someone mentioned it earlier. Svetlana, were you the one who mentioned?
Labor.
Labor. Labor is a perfect example of a positive feedback process, right? There you are with your basketball inside of your belly, pointed face down towards the cervix. And what happens is baby's head pushes against the cervix and the cervix stretches, right? There's the disturbance, baby's pushing against the cervix, and there are stretch receptors in the cervix that measure that stretch. they send that information to our pituitary gland, one of our endocrine glands that is a command center, and it releases a hormone called oxytocin. Oxytocin goes to the uterus and causes the smooth muscle of the uterus to contract. When the uterus contracts, it pushes the baby harder against the cervix, producing a bigger stretch, sending a bigger signal to our pituitary gland, causing more oxytocin to be released. And more oxytocin means a bigger contraction, more stretch of the cervix, bigger signal to the brain, more oxytocin. Notice each time this goes through, the signals get bigger and bigger and bigger and bigger. We are actually enhancing the original stimulus. And why do we want to be pushing bigger and bigger and bigger on the baby?
So the baby has room to come out?
Yeah, to pop the baby out. Absolutely. Right. Notice the goal is the same. The goal in both is to bring the body back into balance. Right. We pop out the baby, mom's body's back in balance. Right. Life is no longer in balance, but mom's body is back into balance. And so the goal is to bring the body back into a balance. We're enhancing the stimulus to bring the body back in balance. A
I
child
have a
birth is,
question.
yes, go ahead.
So in that situation, say like the baby came out, would it go back to a negative system to bring the balance? Is it like that?
No. So what happens is, remember, the disturbance is the stretch of the cervix. Once the baby is expulsed out, then nothing is stretching the cervix anymore. And now that the cervix isn't stretching, it's no longer sending a signal to the pituitary gland. The pituitary gland is no longer releasing oxytocin, and the contractions stop.
Okay.
Yeah. So the body's been brought back into balance. It started with the push on the cervix, and that's right. We take advantage of this with things like Tocin. Right? If you are late-term pregnancy and you haven't started to give birth yet, one of the things they can do is give you an artificially produced chemical that is similar to oxytocin to start that process, start the contraction, start the stretch, start that stimulus, and then it enhances from there. Can someone give me another example of a positive feedback system? Childbirth is one of the primary. There's two other really good examples that most people are aware of. Someone give me another one. Give me at least one more.
Damaged blood vessel.
Yeah, damage to a blood vessel. Absolutely. So what happens is you get a cut in your arm. When you get a cut in your arm, blood is released as a result of that. And that damaged tissue releases a chemical signal. And that chemical signal attracts platelets to the area. And a platelet attaches to the damaged tissue. When it attaches to the damaged tissue, it releases a chemical signal, which attracts even more platelets. And they attach, releasing even more chemical signal, causing even more platelets to come. Notice each time we're enhancing it, getting bigger and bigger and bigger, and we get more and more platelets attached to that damaged tissue until ultimately so many platelets are there. Boom, we formed a platelet plug. Blood is no longer being released from our body, and we've reestablished homeostasis. All right, questions on that? All right, excellent. So those are our positive and negative feedbacks. Here we see some nice examples. And again, these flow charts don't add any new information. These are just, these aren't from your textbook, and I happen to like them, so I think they're useful. Here we see an example of negative feedback, blood pressure, right? Blood pressure in the blood vessels goes up. We have a stretch receptor there. They're stretching more, too much blood pressure, sends the signal to the brain. which sends a signal to the heart. So the heart beats slower, doesn't beat as strong, less blood is pumped out, blood pressure comes down. That would be negative feedback. And we just talked about the oxytocin and the positive feedback of childbirth. All right. And that's our goal as organisms. Our goal as organisms is to maintain homeostatic balance. If we can't maintain homeostatic balance, then what happens is we end up with diseases and death ultimately. Now, when we talk about these disturbances, they are often described as either disorders or diseases. A disorder is an abnormality of function, where a disease is a specific illness. So if I, for instance, have an upset tummy, is that a disorder or is that a disease?
Disorder.
Disorder.
If I have multiple sclerosis, is that a disorder or is that a disease?
Disease.
Right. If I have hepatitis, is that a disorder or a disease?
Disorder.
It is a disorder. Excellent. Absolutely. Right. Now that one was a tricky one because what does hepatitis mean?
Is that inflammation of the liver?
Inflammation of the liver. Now, the reason this was a trickier question is because one of the things that can cause it is a disease like. I'm sorry? All righty. Excellent. One of the things that can cause that inflammation of the liver is the disease like hepatitis A or hepatitis B or hepatitis Z, Z or whatever, which are viral infections, right? Now, in that case, if instead I had said, hepatitis C, then yes, that would be a disease. But I just said hepatitis, just inflammation of the liver. Yes, it can be caused by the virus, but it also could be caused by the fact that I've been drinking vodka for breakfast, lunch, and dinner for the past 3 months. Right. So yes, inflammation of the liver by itself is a disorder because there's multiple things that can cause it. When diagnosing disorders and diseases, we are looking for recognizable signs and symptoms. What is the difference between a sign and a symptom?
A sign is something that the healthcare provider can notice, whereas a symptom is what the patient is reporting to them.
I love that definition. That is absolutely.
These signs, right?
I'm sorry?
I think symptoms can also be signs.
No, and so again, you are I like where you're going the first one. You absolutely have it right, and I love that description. A sign is something that you can observe about someone else, whereas a symptom is something that they have to tell you. Now, again, a sign is objective, like taking a temperature or taking a blood pressure, right? It typically has some type of number associated with it. However, you have to be careful with that because one of the things that happens every time I go to the doctor is they show me that chart with the smiley face down to the sad face, and they ask me what my pain level is. And I say, oh, my pain level based on this is a 6.5 because that, ingrown toenail is really, really bugging the heck out of me, right? Now, there's a number associated with that, but does that necessarily mean that it's objective? Does that mean that it's a sign?
No.
No, because that hangnail that I'm saying is a 6.5 is based on my feeling, right? Whereas Emily, who's hardcore, could have a broken arm and it's probably a 2, right? So again, doesn't just because you can assign a number to it doesn't necessarily mean that it is objective, or that it is a sign. So yeah, signs are typically things that you can observe about someone else, whereas a symptom is something that they have to tell you. I love that definition. It's perfect. Absolutely. And so that's our goal. When talking about diseases and disorders, they can be local or they can be systemic. What does that mean?
Through the body or affecting one particular spot.
Right, absolutely. You're all excited because we're done. We don't have class tomorrow. So when you're done, you go skipping outside to your car to go drive around, and you're skipping out to your car, you roll your ankle. By the time you get to the store to buy the alcohol, it's swollen to the size of a grapefruit, right? But does that affect your hands or your right ear or any other part of your body? No, that's a local effect. Whereas, for instance, especially little kids, when little kids get a fever, right, you can feel that fever over the entire surface of the body. They're just radiating heat everywhere. That's systemic. Absolutely. Now, as I mentioned, our goal is to maintain homeostatic balance. And when that's disrupted, we have disease. It's typically caused by a disease or a disorder. But there's one other major cause of our loss of ability to maintain homeostasis. And what's that other major cause of our loss of ability to maintain homeostasis? There we go. Samuel's got it on the nose. You're all suffering from it right now. Aging. In fact, we define aging as a progressive decline in the ability to restore homeostasis. Give me some examples.
Getting over 30 and getting out of bed and your back hurts.
There you go, exactly, right? Where you can actually injure yourself while sleeping, right? Little kids can sleep on the floor, upside down, hanging from the rafters, and they're totally fine. Whereas now, after you get past 30, you can injure yourself just while sleeping. You can sleep wrong, right? As a teenager, the idea of sleeping wrong is something that is just foreign, absolutely foreign. Give me another example.
Wrinkles.
Wrinkles, the elasticity of our skin. Absolutely, right? You can, if you've got kids like I do, of course, they're much older now, but when they're young kids, one of the fun things you can do with kids is you can actually grab them by the scruff of their necks, carry them around the house, and then let them go. And because of the elasticity, the skin will be back in place by the time Child Protective Services gets there, right? Can you do that to grandma? Can you grab grandma by the scruff of the neck and carry her around the house?
No.
You're likely to rip the skin off of her back. And even if you don't rip the skin off of her back, it's probably going to stay up like that, like a unicorn horn coming out of the back until, I don't know, would it be Old People Protective Services get there? I don't know what that would be. Give me one more example.
Flexibility.
Say again?
Like flexibility.
Sure, absolutely. Flexibility, right? The ability, the flexibility of our joints, the strength of our bones, all of those are examples. Eyesight, the elasticity of our eyes, right? Absolutely. All of those are great examples of things where as we age, there is a decrease, a decline in that ability to maintain homeostasis.
Recovery from the illness is the same?
Yeah, recovering from illnesses, recovering from injuries, absolutely. All of those are great, great examples of them. Spectacular. Excellent. All right. Questions on any of that? All right. That is the end of our introduction. So what we need to do next, like I said, is start working on our foundation, building up our foundation by talking about chemistry. So we went a little long, but I wanted to cover through this material. So what we are going to do next, let's do this. Get rid of that. Bring this up. So we're going to go ahead and take our first break. And after we come back from our first break, we will then dive into starting to build that foundation, our first level of our hierarchy, and that is going to be chemistry. So it is 9:23 now. Let's go ahead and take our full 15-minute break. So what we will do is we will restart the lecture at, it'll be 9:38, 9:39. And I will start the recording at that point. All right. Any questions before we take our first break? All right. I will see you guys in 15 minutes. Any questions before we get rolling? All right. Let's dive into chemistry. Like I said, all the basic things of chemistry, acids, base, ionic bonds, covalent bonds, all those kind of fun things are things that you should have learned coming in here, including how to define an organic compound. An organic compound is, of course, compounds that are composed of carbon and all of its functional groups. And what makes carbon so special and useful in forming organic compounds?
It can form many bonds.
Exactly. And how many in particular?
4.
Yep. 4 covalent bonds. And that allows it to produce very large, very complex molecules, right? So it can form many covalent bonds, 4 each. And again, your book has a nice figure that talks about functional groups, you know, a hydroxyl group and things along those lines. But again, you're not going to have to memorize those necessarily for the exam, but knowing some of these things are things that can be useful as we work our way through this material. Typically, when we talk about organic compounds, they're defined as either monomers, polymers, or macromolecules. Now, how would we define a monomer? What is the definition of a monomer when we're talking about organic compounds? I am speaking out loud, right?
Is that just one bond when
Well,
carbon is bound with one
it
other?
isn't so much one bond, but you absolutely have the right idea. Mono means one. This is a single building block. Right? That's what a monomer is. A monomer is basically a single building block, right? It can be a carbon ring, for instance, for using for making a sugar or something along those lines. Or let's think of something that's more fun, Legos. It's that single blue square Lego, right? It is that basic building block. Now, if instead of just one single blue square Lego, I have 14 of them all stuck together into a row, well, what would I call that row of 16 building blocks that I put together?
A polymer?
Polymer.
Yeah, that would be the polymer, absolutely. However, if I'm playing with Legos, am I limited to just blue squares?
No.
No, I've got, you know, orange rectangles and red triangles and all sorts of others. So I can take all these different types of building blocks, put them together into big complex looking structures. And those are our macromolecules, right? So when we're talking about organic compounds, those are basically the orders of organization for them. What we're going to care about mostly, because they have the greatest effect on the function of our cells and therefore allows us to move up to the next level of our organization, are the macromolecules. Macromolecules are vital for both the structure and the function of the body. And macromolecules come in 4 flavors. What are the 4 main types of macromolecules? Someone give me an example of a type of macromolecule found in the body.
Proteins.
Excellent.
Fats.
Well, hold on, let's do one at a time. Proteins. Absolutely. Proteins. Excellent. Right? Perfect. What was the other one? Fats, although fats is kind of the common term for that. What is the appropriate term for fats? There we go. Lipids. Perfect. Which you're right, absolutely are indeed the fats. What are the proteins?
Amino acids.
Well, they're the building blocks that make it, but proteins are pretty much proteins. There you go. Tony's got the next one, carbohydrates. But again, remember, no abbreviations in this class because spelling counts. So, but if lipids are fats, what are our carbohydrates?
Sugars.
Sugars, excellent. And what is the 4th macromolecule? There we go. Same. Yep, nucleic acids. Excellent. So those are our 4 main, and now that I've bothered to write this, I can erase it because we can then do that there. Our 4 main types of macromolecules: carbohydrates, lipids, proteins, and nucleic acids. All right, let's talk about each one of these. Starting first with carbohydrates. Carbohydrates, like most of our macromolecules, have many functions, but what are the 2 primary functions of our carbohydrates?
Energy.
Energy, absolutely. One of the major functions of carbohydrates is to provide energy. In fact, many of you took advantage of that this morning. You had that nice big baked potato for breakfast, or that nice big bowl of cereal for breakfast, where it was provided lots of carbohydrates to give you that sugar. But you know where else there's a tremendous amount of carbohydrates? That green grass in your backyard. How many of you had a big bowl of green grass in your backyard for breakfast this morning? Not too many of you. Why not? There's plenty of carbohydrates in there.
Stomachs can't process it.
Right, because it is structured, I mean, it's specialized for structure, right? Provides energy and it provides structure, right? Out there in the grass, that is providing structure, right? Cows can eat it, but they have like 87 stomachs, right? And they're constantly swallowing it and spitting it back up and swallowing it into a different stomach, things along those lines. So it's providing that structure in that case. So carbohydrates can provide energy and they can provide structure. So they have lots of functions, but those are two of the huge ones. Carbohydrates are primarily composed of carbon, hydrogen, and oxygen. But the real key to carbohydrates is that they have a 2-to-1 ratio of hydrogen to oxygen. Right? And it is that 2-to-1 ratio that is key for defining our carbohydrates. And not surprising, when we're identifying our carbohydrates, we do them based primarily on size. The most basic of our carbohydrates are what we call our monosaccharides. Monosaccharides are made of either 5 or 6. So here we have our hexagon where those 6 carbons, at the corners, or they can be pentagons with 5 carbons at all the corners. So basically they are 5 or 6 carbon rings with functional groups of some sort coming off of them. And these include things like glucose and fructose and galactose and ribose and deoxyribose. Notice with these carbons and the 4 bonds that they form, they are able to store a massive amount of energy. So yes, these are building blocks that we use, the Legos we use to make bigger carbohydrates, but these are the things that we can effectively and efficiently break down to produce the energy, right? And when we're breaking down these carbohydrates, we convert the energy from that into a unit of energy that our body uses to function. And what is that primary unit of energy that our body uses to function?
ATP.
ATP, excellent. All right, so we're going to use that energy to make ATP. Spectacular. However, we want to also take these monosaccharides and combine them together to form our disaccharides. Now, again, this occurs in a process we call dehydration synthesis. Let's go ahead and cheat and go back to our whiteboard. I'll do a really, really simple example of this. Here we have 1 monosaccharide. Here we have 2 monosaccharides, and these often have hydroxyl groups as functional groups associated with them. When we want to form a bond between them, what happens is that these 2 will come together and there will be an oxygen that holds them together. So notice during that process, we lose a hydrogen, we lose an oxygen, and we lose a second hydrogen. And we end up here with a molecule that is known as dihydrous monoxide. What's the other name for dihydrous monoxide?
Water.
Water. So notice when we're forming that bond between them, we are drawing water out of it. So we call that dehydration synthesis. Conversely, if we wanted to break a bond between 2 monosaccharides, if we wanted to break this disaccharide apart, then of course that means we need to add water to it. We add that water to it, And in that fashion, we're able to break it apart, separate the two. So we're using water to split the molecule. And so that is called hydrolysis. Hydro, water, lyse, to split. So when we're doing these types of formations, as you should know, we're going to use dehydration synthesis and hydrolysis. And if you didn't like my amazing pictures that showed this, here are some pretty pictures showing this process. Notice we can see here that again, when we're forming that bond, we are drawing the water out, or when we're breaking that bond, we're using water to split it. And we can do this to form many, many important disaccharides. For instance, we can take a glucose and a fructose and put it together and make a sucrose. What makes sucrose so important? Where might you find it?
Sugar.
Okay,
Table
but
sugar.
well, these are all sugars, right? So what's specific about, what do we commonly think of sucrose as? Where might you find sucrose? Thought this would be one of the easier questions.
The table sugar, right?
Yeah, it's table sugar, absolutely. So one of the places you find it is Starbucks, right? Where you can pour half of a gallon of it into your Starbucks coffee to make it palatable. Excellent, right? Or, for instance, we could take glucose and a galactose and put it together to form lactose. Where might you find lactose?
Milk.
Milk, absolutely. Conveniently enough, also at Starbucks. However, probably the most vital for human existence, you can take two glucoses and put them together to form a maltose. And what makes maltose so vital for human existence?
Beer.
There you go. You use it to malt barley so that you can make beer. Absolutely. Without maltose, you don't get beer. Right? Without beer, you don't get a sane instructor for this class. So again, vital for human existence. We have all of these monosaccharides that we put together to disaccharides. And the monosaccharides and disaccharides together, we call simple sugars. So these monosaccharides and disaccharides together form what we call our simple sugars. However, like I said, those are really easy to use for energy. They have lots of bonds that can be broken, releasing lots of energy used to make lots of ATP. But we want to be able to store that energy as well. And to store that energy, or to provide that structure that we talked about, we need our polysaccharides. And we already talked about the great example, the easiest example of this when we're talking about plants. That big difference between the potato and the grass out in your backyard is how they store their carbohydrates. The potato stores its carbohydrates as what? There you go, same as got it, starch. Right? Starch is the form that is easily digestible, broken down for energy. Whereas the grass stores its carbohydrates in what form?
Cellulose.
Cellulose, absolutely. We talked about how the cow and its 87 stomachs that are necessary to break it down. Another great example is a sheep and a wolf. A sheep and a wolf are very similar in size, but the digestive system of the sheep is 2.5 times as long as the digestive system in the wolf. Why? Diet. What does the sheep eat?
Grass.
Grass. What does the wolf eat?
Sheep.
Yeah, it eats the sheep. It eats meat, right? Absolutely. Those proteins are much easier to break down. It has a much simpler digestive system. Again, it is much harder to extract the nutrients out of that grass. So the sheep has a much, much longer digestive system so that it can process it and get the nutrients it needs. Now, plants have both forms, starch and cellulose. Humans Animals only store carbohydrates one way. So which do we use? Do we use starch or do we use cellulose? How do animals store carbohydrates?
Starch.
Starch?
Animals or us as humans?
Both. Animals,
Both.
we are animals, so how do animals store their carbohydrates?
Glycogen.
There you go. Neither starch nor cellulose. You're absolutely correct. Animals store their carbohydrates in a third form of polysaccharides known as glycogen. So here we see some examples of glycogen. Glycogen is basically where we take a massive number of glucose monomers and put those glucose monomers together into these big, huge, complex, elaborate branching structures known as glycogen. Obviously, every cell of the body has some glycogen in it, has some fuel reserves, but which tissues in particular have a large amount of glycogen stored in them?
Or muscles?
Muscles, absolutely. Muscle, because they use massive amounts of ATP when they're contracting, have a massive amount of glycogen in it. Anyone guess another one, another organ that would have a massive amount of glycogen in it? Liver, there you go, excellent. Absolutely, the liver actually stores glycogen so that as you're not eating, it can actually, if glucose levels drop, it can actually release that stored glucose to maintain appropriate glucose levels in the body. Excellent. So yeah, most cells have this, but definitely muscle, definitely liver cells have massive amounts of that glycogen stored there for important uses. All right. Carbohydrates are vitally important, right? Not terribly fun, but they are vitally important. So that's what we need to know about them. Let's move on to something slightly more interesting, and those are our lipids. Lipids are similar to carbohydrates in that they have, they're primarily composed of carbon, hydrogen, and oxygen. But the one big difference between a lipid and a carbohydrates is the ratio of hydrogen to oxygen. Our lipids have very few oxygen in relation to hydrogens, much, much more hydrogen. Why is that important? What do you know about oxygen?
That we need it.
True. Well, we need all of these things. Absolutely. But from a molecular standpoint, carbon, hydrogen, and oxygen all form covalent bonds. Someone remind me again what it means to form a covalent bond?
That they're sharing electrons.
They're sharing electrons. And what do you know about oxygen when it comes to sharing?
It doesn't have a full valence shell.
Well, true. I mean, that is why it shares, but does it, how good of a sharer is oxygen? Well, so if I've got, so let me, maybe I'm not making myself clear. So here I have a hydrogen and here I have an oxygen, and between the two of them, they're sharing 2 electrons, right? Now, normally when you and I think of sharing, right, we share evenly. Is that how oxygen feels about sharing?
It's electronegative.
Right.
No.
No, oxygen's a 2-year-old. And how good are 2-year-olds at sharing?
Horrible.
Horrible, absolutely. And that is indeed the case with oxygen. As we know, oxygen, right, tends to hoard the electrons, keeping it more towards it than it does for the hydrogen. And as someone mentioned, that is why it has a partial negative charge to it. That happens to also give the hydrogens associated a positive, partially positive charge. It's one of the things that makes water so magical, right, is that it has polarity. That's why it has surface tension. That's why it hurts while you do the belly flop. That's why insects can skitter along the surface of it, right? It's why it expands when it freezes. There's all these magical qualities to water, and that is because water has polarity. And the reason it has polarity is because oxygen doesn't like to share. But here we have these carbohydrates that don't have a lot of oxygens in them. mostly carbons and hydrogens, and carbons and hydrogens do like to share. So what's the implication of something that is does like to share when it comes in relation, for instance, to water? I'll be honest, it warms the cockles of my heart that you guys don't know a lot of chemistry, because as far as I'm concerned, chemistry is stupid. Nothing good has ever come from chemistry, but there are some of these concepts that we do need to understand. Right? Water is polar. Oxygen, because it doesn't share those electrons evenly, produces polar bonds. However, carbon and hydrogen share equally. They produce non-polar covalent bonds. And do polar things and non-polar things like each other?
No.
No, you may not have ever thought of it that way before, but when you go to have lunch today and you're having that salad and you grab the Italian dressing out of the refrigerator, what's the first thing you do?
Shake it up.
You shake it up. Why do you shake it up?
Separate.
Yeah, because the water and the fats have separated, because fats don't like water. They're hydrophobic. And so that's why I have to shake it up to mix it back up again. And that's the key with lipids. Because they have so few oxygens, they have few polar covalent bonds, and they're primarily hydrophobic. They don't like water. Right? Now, unlike carbohydrates, there are lots of different versions of these in our body. I'm not going to list them all, but I do want to talk about some of the more common or basic ones. And then as we work our way through the class, we'll talk about more as we come along them. By far the most common lipid that we find in the body is a triglyceride. Triglyceride is also sometimes referred to as a neutral fat. And what do you think you can tell me about a triglyceride?
It's 3 fatty acids with a glycerol backbone.
Yeah, absolutely. It has an alcohol, in this case, glycerol. And then coming off of that, it has not 1, not 2, but 3 fatty acid tails. You're absolutely correct. So we have this big, large, complex structure. I think I have a pretty picture that shows this nicely. Right, here we go. We have an alcohol, in this case, glycerol. 3 fatty acid chains comes together to form a triglyceride. Now, again, you don't need to know the chemical composition of a glycerol, but we do need to have a basic understanding of this centralized type of structure. And one of the ways we can easily identify that is with these illustrations or these symbolic things. And what I want to talk about first are these fatty acid tails. Notice these fatty acid tails are primarily made up of carbons. As we know, a single carbon is capable of forming 1, 2, 3, 4 covalent bonds. And notice with this particular fatty acid, every single carbon has the maximum number of hydrogens that it could be associated with them. This is what we call a saturated fatty acid. However, notice something interesting has happened here. Here, we have formed a double bond between 2 of the carbons. This does 2 things. Notice it causes a kinking or a bending of the fatty acid. And notice also this, because of this double bond, doesn't have the maximal number of hydrogens we could have on this fatty acid. This one happens to have 1 double bond, so we call it a monounsaturated fat. If this one were to have a second double bond, guess what we would call it then?
Polyunsaturated.
A polyunsaturated fat. Excellent. Now notice when we look at the illustrations like this, it is easy to tell what's saturated and unsaturated. We can see the chemical composition of it, something like this, or we can see it here with the symbolic representations with that bend in it. However, most of you don't have microscopes at home. Most of you aren't capable of looking directly at the fatty acids in your houses. So how can you typically tell which ones are saturated and unsaturated when you're roaming around your kitchen?
Solid compared to liquid.
Which is which?
Saturated is solid at room temperature. Poly and mono. Poly is oily, liquidy.
There you go, exactly. Basically, because of the kinks in the fatty acids, the unsaturated fats don't line up as easily as the straight saturated fats are. So saturated fats are typically solid at room temperature, things like butter, things like lard, whereas things like olive oil or canola oil or things along those lines, because of their unsaturated fatty acids, don't line up as easily, and so they're typically liquid at room temperature. Of course, if you take that olive oil and put it in the fridge and leave it in there long enough, will it eventually line up and solidify? This is the part where you say yes.
Yes.
Yeah,
Yes.
absolutely. Yeah. So if you put oils in there, that can eventually happen. Absolutely. Excellent. All right. Notice again, what do we use these triglycerides for? What is their function?
Cooking.
True, we use it for cooking. Why do we use it for cooking? Why do we put it in our food?
Flavor.
True, definitely it does provide some flavor, but
For
notice
heat.
well, it can withstand heat. I like where you guys are going with this, but I think you guys are overthinking it a little bit, right? Notice that again, when we look at one of these single fatty acids, look at the massive numbers of bonds. Remember, basically our job of our body is to break these bonds. When we break these bonds, we release that energy. And when we release that energy, we can use that energy to make ATP. So the primary function of these triglycerides is to store energy. Right? Actually, we get more energy from a fatty acid than we do from a carbohydrate. So then why don't we just use fatty acids to make our energy? Why do we rely on carbohydrates? That means the lipids must be doing something else as well. What else can these triglycerides do for us?
Make up cell membrane.
Say again?
Make up cell membranes.
Sure, absolutely. We use lipids for that. We don't use triglycerides for that. We will talk about those. We will get to those, but those aren't the triglycerides. What do we use triglycerides for?
Insulation.
Insulation, absolutely. We store it everywhere. It's protecting our kidneys, where it's found within the tissues of our skin, and it's found underneath our skin, right? Providing that protection, providing that insulation. That's what I keep trying to explain to my wife. I'm not fat, I'm just protecting my internal organs, right? So again, we have that, natural insulation, that natural protection, and that energy. Again, vitally useful, vitally important, but not nearly as interesting, as someone pointed out, as our phospholipids. Phospholipids are a type of lipid that we use to form our plasma membranes of our cells. Right? We haven't gotten to our cell anatomy yet, but when we get to our cell anatomy, basically a cell looks like that. Right? And this line that we draw is what is known as the plasma membrane. And the plasma membrane is comprised primarily of phospholipids. Phospholipids are similar to triglycerides in that they have a large head region and then fatty acid tails. However, the fatty acid tails for our phospholipids just have 2 fatty acid tails. It makes it much easier. Now, actually, one of them is actually kinked, so let's go ahead and cheat. It's the first time I draw it. We'll draw it like that, but normally I just draw them in straight lines because it's easier. But we have this 2 fatty acids tail and this head region. So one of the big differences between the phospholipid and the triglyceride are the number of fatty acids. There's only 2 fatty acids instead of 3 for the triglycerides. But there's one other really important part to this phospholipid. The tails, as we know, are almost exclusively carbons and hydrogens. And so as we know, this is, of course, nonpolar. This is hydrophobic. But what is interesting and unique about phospholipids is that their head is actually polar. It actually likes and can interact with water, which is useful because, as we've talked about, there's lots of water outside of the cell. So what our phospholipids are able to do is, when forming this plasma membrane, they have that big head that points out away from the cell so that it can interact with the water that's outside of the cell. And it has its it has its fatty acid tails pointing inward because the inside of the cell doesn't like water. All right, questions on that? You all are really going to let me get away with saying that the inside of the cell doesn't like water? No one's going to call
No,
me
there's
on
a
that?
there's a double layer.
Yeah, you got the right idea. There is absolutely water inside. Inside the cell as well. And again, you've spoiled my fun, but you're absolutely correct, right? So then usually this is the point where I say, well, it must be pointing inward, right? Where they must be pointing inward. So they've got the circles pointing this way and the fatty acids pointing out. Well, how can it do both? So then do we alternate where we have them going, right? One pointing one direction and the other pointing the next direction? No, that's not how we do it. You've hit it on the head. The way we actually do this is by having, a double layer, not 1, but 2 layers of phospholipids that arrange so that the heads point out and the tails point in, right? Heads out, tails in. This is the way these things are going to be organized, and they form a double layer of phospholipids that allows water to interact with the wall of the plasma membrane from the inside, water to interact from the wall on the outside. But at its core, we have this hydrophobic fatty acid region, which can form a barrier, limiting what can get inside and what can get outside of the cell. And again, I've done a crappy job of drawing this, but we have some pretty pictures from your textbook that shows this. Here, again, we see the chemical composition, which again, you don't have to memorize, but just recognize the symbolic illustration of it, the single head with the 2 fatty acid tails. And as we mentioned, here we can see how we have a double layer of these phospholipids arranging so that outside the cell, the heads can interact with the water and the stuff that's in the water. Inside the cell, the heads can interact with the water and the stuff that's dissolved in the water. But again, we have this nice fatty acid middle region that is hydrophobic and forms that physical barrier, limiting what can get inside and outside of the cell. We will talk about these phospholipids and their function in much more depth when we get to our cell unit, the next unit, which we'll be doing in the next class. All right, questions on phospholipids? All right, now those are 2 primary types of lipids, but as I mentioned, there are lots of them. Here, for instance, we see a cholesterol. I know normally I say cholesterol and everybody boos and hisses because they think cholesterol is a bad thing. And there is such a thing as bad cholesterol, but cholesterol is very important for many other things as well. We use cholesterol. Notice cholesterol is very distinct because it has that 4 carbon rings and its functional groups. Cholesterol can be used to make things like bile salts, and it can be used to make things like hormones. For example, here we see two examples of two hormones. Move everybody over here so we can see this a little more clearly. And notice they both have that same 4 carbon ring to them. And notice their functional groups are almost identical. That must mean that these two hormones are almost identical as well, right? And can be easily just mixed up in your body. You could use one for the other interchangeably.
No.
No, in fact, one of these is estrogen, and really estradiol, and the other is testosterone. There aren't many hormones in the body more different than those. One turns girl-like people into women-like people. One turns boy-like people into men-like people. So notice even subtle changes in those functional groups can have massive influences and effects on the development of the body. So these hormones are vitally, vitally important. And like I said, there are other types as well, right? One of the issues that we have is that lipids are hydrophobic, and we need to transport them throughout our body. And how did we say we transported things in our body? What does the transporting of things in our body?
Blood.
Blood. And what is blood primarily made up of?
Water.
Water, absolutely. So do we want to take all these fats that we want to transport and just pour them into the water of our blood and hope for the best that they're going to get where we need them to go? No, that would be a very bad thing, right? It's the same reason you don't pour your bacon grease down the sink, right? Because all that fat would congest and clog it and would be a bad thing. But we do need to transport it. So the way that that occurs is involving things like lipoproteins. Notice here we see an example of a lipoprotein where we have a bunch of fatty acid tails. And these bunch of fatty acid tails are actually attached to proteins, water-soluble proteins. So we put this nice candy-coated shell of water-soluble proteins on the outer surface. So this is a structure that can actually be dissolved in water and can transport all of these fatty acids where we need them to go. So like I said, there are dozens of different types of lipids that we can find in the body. These are just some. And like I said, we'll talk about more as we get to them. All right. Questions on that?
Nope.
All right. Excellent. Oh, and again, your book's got a nice table that talks about all the different ones as well. So we did that. Excellent. All right. Now, let's talk about proteins. Again, all of these macromolecules are vitally important, but probably one of the most important ones are indeed our proteins. Proteins are comprised of amino acids. There are 20 amino acids, and no, you do not need to memorize your 20 amino acids. If you want to do that, then take a molecular biology course. But one of the key differences between proteins and lipids and carbohydrates is that while all of them are comprised of carbon, hydrogen, and oxygen, proteins also have a large amount of nitrogen in them as well. Now, I mentioned how proteins are so vitally important, but then underneath here, it shows that they only make up little less than 20% of your body weight. And that doesn't sound like a whole heck of a lot until you remember in the last class that I said 60% of your body weight is water. So that means you're only 40% stuff. And half that stuff is proteins. Proteins are vital for producing who and what you are. They are by far the most diverse in structure of our macromolecules. And if they're the most diverse in structure, what does that tell you?
Very important.
True, they're very important, but if they're diverse in structure, what does structure relate to?
Energy.
Not energy in this case. The structure
Stability.
of something affects the function. There you go. Samuel's got it. The function. The structure affects the function. If they're the most diverse in structure, that means they're the most diverse in function as well. We can talk about this in lots of different ways by talking about some simple examples. The most common protein in your body is collagen. If you were to reach into your body and randomly pull out a protein, absolutely, we'll talk about those in just a second. But the most common protein is collagen. Collagen is comprised of 3 rows of amino acids that are basically wrapped around each other, kind of similar to like threads in a rope. And that helps us to understand their function, because remember, their structure determines their function. Right? Again, I have to work on my analogies for this because they don't always work online, because normally we're sitting in the classroom and I'll point my arm down the middle of the classroom and say, I'm going to put half of you on one side, half of you on the other, throw a rope out into the middle, and we're going to spend the next hour of class playing tug of war. And as I look at you guys on your cameras, as fit and healthy as all of you look, if we got half of you on one side and half of you on the other, all pulling on this rope, are you guys going to be able to tear that rope in half?
No.
No, because it has a tremendous amount of what we call tensile strength. That tensile strength is that ability to resist tearing or shearing forces. Notice this strength doesn't come from rigidity. It's not rigid. When you guys are done playing tug of war, I can roll that rope up into a ball and throw it into the trunk of my car. Well, that's how collagen works, right? When I grab the skin and pull on the skin, it doesn't tear away because I have those collagen fibers providing that tensile strength, resisting the pull of that, right? But if my lips are not full enough and I want to look more like Angelina Jolie, what can I do? I can inject them with collagen, causing them to swell and enlarge, but do they become rigid as a result of that? No, right? They still have that flexibility. So it has that tensile strength, that support, that structure that collagen provides, but it doesn't come from rigidity. This protein is very, very different from another protein called hemoglobin. What does hemoglobin do?
The blood.
Yeah, it's in
Transports the
blood.
oxygen in the blood.
Exactly. It's in the red blood cells and it carries oxygen. In fact, it's what makes the red blood cells red. Because in hemoglobin, unlike collagen that is comprised of 3 rows of amino acids, hemoglobin is comprised of 4 subunits. But with the subunits of hemoglobin, they're globular. So they're these basically block-shaped proteins, globular proteins, that line up together, all these squiggly globular proteins. And what's special about them is at the very center of them, they have what is called a heme group. And that heme group has an iron at the center of it. And that iron is what binds the oxygen, allowing that oxygen to be transported through the body. A single red blood cell has somewhere on the order of 250 million hemoglobin inside of them. And each one of those hemoglobin have 4 heme groups that can hold 4 oxygens. So how much oxygen can a single red blood cell carry?
Close to 1 billion.
Yeah, or a lot. I don't know. I can't do math, but it's definitely a lot, right? Absolutely, a lot. So it's a massive amount. And a single drop of blood, right, has somewhere around, 100 million red blood cells in it. So again, we're talking about crazy high numbers here, but very different structure, very different function of these. But as someone else mentioned, Samuel looks like mentioned, probably the most important type of proteins found in the bodies are enzymes. Enzymes act as a catalyst. Someone remind me again what a catalyst is?
Speeds up reactions.
Yeah, it facilitates chemical reactions, speeds them up, typically by lowering the activation energy, making it easier for that chemical reaction to take place. Now, one of the things that we will learn in anatomy and physiology is in anatomy and physiology, you practically never say never, you never say always. right? Because there's always exceptions. Life is weird and funky that way. However, up to this point in time, every single chemical reaction that has been studied in the human body has an enzyme that helps to facilitate it. Doesn't mean that every chemical reaction that takes place in the body uses an enzyme, but every chemical reaction that takes place in the body, we have found an enzyme that makes it easier to do. Maybe some point along the line, we'll find one that doesn't, but it hasn't happened yet. Now, again, some of these can be pretty simple. Lactase is a great example of an enzyme. What does lactase do?
Breaks down, helps speed up lactose.
Yeah, it
digestion.
helps in the breakdown of lactose. Remember, we saw that lactose is a disaccharide made up of 2 monosaccharides, and lactase helps us to break those down, helping you to be able to break down your milk products, allowing you to drink milk with your cereal, allowing you to have ice cream for dessert, right? Things along those lines. If you have problems where you produce a non-functional form of lactase or you don't produce enough lactase, what do we call you?
Lactose intolerant.
Right, or very sad because you can't eat ice cream, right? So exactly, lactose intolerant, right? Again, not being able to eat ice cream is probably not the worst thing that's ever happened in the world, but there are other chemical reactions that are vital for human existence. And if we don't have those enzymes, that can cause major, major problems. All right, so again, all of these different proteins have different shapes, and their different shapes determine their function. So understanding the function of a protein starts with understanding how they are formed. And that's what we're going to need to do next. We are going to need to understand the structure of our proteins. Now, proteins are made up of the building blocks, so we mentioned those amino acids. Notice they're put together in the same fashion of what we saw with our lipids. We use, with our carbohydrates, we use dehydration synthesis and we use hydrolysis to form them. But again, they have to name things. So when we use that dehydration synthesis to form the bond between the amino acids, we call that bond a peptide bond. Once we put two amino acids together, we have what we call a dipeptide. And when we put about 10 to a couple thousand together, we call them polypeptides. And those polypeptides are then used to form our proteins. We kind of need to understand how this works. So we are going to go through the levels of structural organization for a protein. Now, I think this is probably the densest stuff, the densest material, the least fun material we have to cover today. So I think this is a good part, even though it's a teeny bit early, I think this is a good part to take our second break. So let's go ahead and take our second break. We will restart at, let's see, 15 minutes from now. So that is going to be 10:43. And I will start the recording at that point so that we can come at this fresh and hopefully make sure that it makes sense. So I think this is a good stopping point for our next break so we can get some coffee, get a drink. Any questions before we take our next break? All right, excellent. Then I will see you guys in 15 minutes. Caffeinate so that you're ready to go when we come back. See you in 15 minutes. Let's go ahead and get started. We were getting ready to talk about the levels of structural organization of proteins. And we will go through the pretty pictures from your textbook and all of that in a minute, but I think sometimes it's useful to actually take the time to kind of draw and write these things out. Now, as we know, at its most basic level, or what is basically the primary level, right? So 1 prime. Basically, actually, let's make this a little bit smaller so it'll all fit. Proteins are comprised of sequences of amino acids. And that's what the primary level is, just a sequence of amino acids. Right? So what happens is we have amino acid 1, and it is connected to amino acid 2. Whoops, that's not a 2, which is connected to amino acid 3, which is connected to amino acid 4, and that's still not a 4. That's not a 4 either. There we go. And so on and so forth. So as we put this together, remember we're forming those peptide bonds between these, and that gives us a sequence of amino acids. And at its simplest, most basic level, that is what a protein is, a sequence of amino acids. Now, again, just because this is the simplest, just because this is the basis, doesn't mean that it isn't important, or is it? The average protein is made up of literally thousands of amino acids. So if I just change one single amino acid in that chain of 10,000 amino acids, can that really make a difference?
Yes.
Yeah, absolutely. Right? How many people here have heard of sickle cell anemia? A lot of head shaking, absolutely. Sickle cell anemia is a condition where that globular protein that we talked about, that hemoglobin, has one amino acid in it changed. And that change of one amino acid causes that hemoglobin, which is normally globular in shape, when it gets to a low pressure environment, like inside of a capillary, it causes the protein to straighten out. And as the protein straightens out, it causes the red blood cell to straighten out, forming that C or sickle shape to it. It can also cause the red blood cell to rupture, releasing all of that hemoglobin into the capillary, congesting the capillary, causing damage, lowering the blood carrying, the oxygen carrying capacity of the blood, causing pain, causing damage. Yeah, it is a painful and can be serious condition caused by the simple change of a single amino acid in a chain of thousands of them. So yes, while the primary level is simple, it is still very important. Just like the alphabet, right? If you're writing a sentence and you change one letter, it can completely change the meaning of that sentence. And it's the same thing here as well. Just changing one amino acid can have a dramatic change and effect on the level. Now, the other thing, not only the reason, let's say it this way, the reason we have to have the correct, and let's go ahead and erase that. Oops, not that one, just the arrow. The reason that this matters so much is, again, while we don't need to know everything about our amino acids, we do know that amino acids have functional groups. Some of these functional groups can be positive, and some can be negative. And what do we know about positive and negative things?
They attract each other.
They can attract each other, absolutely. So what can happen is this positive thing can be attracted towards this negative thing. This negative thing can be pulled towards that positive thing. And it can actually cause our amino acid sequence to bend. Or conversely, we could have two negative functional groups next to each other. What do we know about negative things?
Repulse.
They don't like other negative things, exactly. So what could happen is these two could push away from each other. And as they push away from each other, it could cause our sequence of amino acids to bend in the other way. And it's not just the ones that are next to each other. Ones that are further away can interact with each other as well. So a positive from this one here could be attracting a negative one much further down the line, bringing those two together. These types of local interactions are what we call the secondary level. This secondary level is basically local interactions of functional groups. And these local interactions of functional groups causes change in the shapes. Yeah, oh, that's really bad. in the shapes of the sequence. All right. I'm going to draw some very simple ones here, but then I'm going to cheat and go back to your lecture for a second so that we can see this. An example of one of these would be where you get these coils of the sequences that form. These are called alpha helixes. There are some where they will arrange up in this linear fashion that are called beta sheets for some examples of this. And like I said, let's cheat and go to the lecture because they do a better job of showing this. Notice here we see our primary structure, just the sequence of amino acids. Here is that secondary structure. Notice again, here is that example of the alpha helix that is forming, or these beta sheets that are forming. And notice it is caused by these local interactions of their functional groups being attracted or repulsed to each other. In fact, we have a name for these types of interactions, right? These types of interactions where things are attracted to each other in this fashion are what we call hydrogen bonds. So these are formed by hydrogen bonds. So the hydrogen bonds between these functional groups cause the effect of these shapes to take place. All right. You with me so far?
Yep.
Excellent. Now, notice as I mentioned, and one of the keys that I've been emphasizing on this is that these are local effects. They occur in just one part of the sequence of amino acids. So say, for instance, you could have a sequence of amino acids that has an alpha helix to it in one part, has a beta sheet in a second part, and then a second alpha helix in the third part. Each of those individual parts, those local parts, are secondary structures. But notice when you put all those secondary structures together, then you have basically the three-dimensional organization of this sequence of amino acids. And that is what the tertiary level is. The tertiary level, conveniently enough, is the three-dimensional shape of the entire sequence of amino acids. And that's what we have with the one that I've drawn there. So tertiary is the three-dimensional shape. That makes it convenient and easy to remember. However, notice I keep using the term sequence of amino acids, right? Or we could also use the term that this is a single polypeptide. I make a point of emphasizing this. I haven't used the term protein yet. And the reason I haven't used the term protein yet is because typically a protein is made up of two or more subunits. Remember, I mentioned collagen has three rows of amino acids, three subunits. Hemoglobin has 4 subunits to it. So a typical protein is not made up of just one row of amino acids. Yes, I have a three-dimensional shape here that is our single polypeptide, our single sequence of amino acids. But to make a fully functional protein, we need that quaternary level. The quaternary level is where we take multiple subunits and we put them together into a fully functional protein. So notice I have my first subunit here, but then to that, maybe I want to add a globular subunit, and maybe to that, I want to add a more linear subunit. And when I put those all together, I get a fully functional protein. So notice we started from a single sequence of amino acids, and now we have a multi-subunit, fully functional protein. Questions on that? All right. There's one last important concept that we have to talk about here that is vitally, vitally important. Notice I have this fully functional protein, this quaternary level that is formed by all of these things coming together, giving it its shape, giving it its structure. But ultimately, where does the shape come from? The fully functional three-dimensional quaternary structure of this fully functional protein, where does its shape come from?
Bonds.
What kind of bonds?
Hydrogen.
It's formed by hydrogen bonds. And what do you know about hydrogen bonds? Super strong, stand up to anything?
They're not strong.
No, these are by far the weakest of our bonds. And in particular, they are very sensitive to what two things?
Temperature.
Temperature, and what else? What else, sir? Go ahead.
Pressure.
No, not pressure, although that's a good guess. Temperature and
What?
pH. They're highly sensitive to temperature and they're highly sensitive to pH. So if you increase the temperature, you change the pH of the environment that that protein is in, what's going to end up happening is that it is going to change the shape. It's going to change the structure of your protein. And if you change the shape of your protein, right, structure affects function. And if you change the shape of that protein, suddenly it's not going to work anymore. Right? If we modify the hydrogen bonds, we change the shape, and therefore the function of the protein. And what do we call that process where we use pH and temperature to change the shape of the protein when that occurs? What do we call that? What have we done to the protein? Jacob, I think you said it, but you didn't say it on the mic. Say it again.
We denatured it.
Exactly, right? Many of you did that with your egg this morning for breakfast. You denatured the protein. And when you denature that protein, you change the shape, right? We talked about body temperature before and how important it is to maintain it. One of the reasons we have to maintain that tight restriction is because changing the body temperature can affect our enzymes. When we get sick, we get an elevated temperature, 101, right? 105, not 105, 100.5. And that helps to protect us from the pathogens. However, would 105 be a good thing? 110, more temperature is better? No, because if our temperature gets too high, then we start to denature our proteins, like those enzymes we talked about that are vital for our function. So in this fashion, we have this very important structural organization that not only helps us to understand how we get the diverse shape, the diverse function, but it helps us to understand that how it's just those weak hydrogen bonds that are forming it. So it helps us to understand why we have to keep such tight control of our pH, such tight control of our body temperature, so that our proteins function properly. And again, my protein here is truly awesome, but we have the pretty pictures from your textbook that show this as well. They do a great job, as we talked about, of showing here our secondary structures. Those alpha helixes and beta sheets all come together to form our tertiary structure. And remember that tertiary structure just basically forms one subunit. And then we put those subunits together with our quaternary structure to produce a fully functional protein. And again, as you guys pointed out, we modify or change or break those weak hydrogen bonds, and it leads to the denaturation, the distortion or the change of the shape of the enzyme, which absolutely can change its function. All right. And again, you probably haven't thought of it in these terms, but you're aware of it because one of the fun things you do when you have kids is that you'll take a small piece of white bread, take a paper towel, dry off their tongue, and put that piece of white bread on their tongue, and they let it sit there. And when they let it sit there, what happens? Anyone ever done this themselves or with their kids before? What happens if you just let a piece of white bread sit on your tongue for a while?
Disintegrates or?
True, it starts to dissolve it and break it down, but in particular, what do you experience when you do this?
It gets sweet.
Yeah, you get sweet. Why does it get sweet? Anybody know? Emily is 100% correct. It gets sweet because what's happening is your tongue produces, you got the right idea, Terrence, your tongue produces a special enzyme called salivary amylase. And what salivary amylase does is it breaks down carbohydrates into simple sugars. That bread is a complex carbohydrate. It is a starch, but our salivary amylase starts to break it down into simple sugars. And as it breaks it down into simple sugars, you can taste the sweetness of that sugar on your tongue. You then swallow that bread into your stomach. And when you swallow that bread into your stomach, does that salivary amylase keep breaking down the bread inside of your stomach?
No,
Why not?
the hydrochloric acid
Change the
denatures
pH.
that protein.
Yeah. What's the pH in your mouth? Anyone know?
7,
Yeah, it's about 7. What's the pH in your stomach?
1.
Acidic?
Yeah, 1 to 2, very acidic, exactly. So when that salivary amylase gets swallowed into your stomach, the change in pH causes it to change shape, and when it changes shape, it's denatured, it's no longer functional. All right, excellent. Hopefully these things make some semblance of sense. Questions on this structural organization of proteins? All right, excellent. Stunned silence, of course, to me means that you guys understand it perfectly and I should continue forward and in fact also go faster. So just so you guys know, that's how I interpret silences. All right, excellent. So As we mentioned, proteins are vital for many functions. They have the most diverse structure, so therefore the most diverse functions. But as we also talked about, one of the most important functions is to act as enzymes. As we mentioned, enzymes are a biological catalyst. And as we talked about, it speeds up a chemical reaction, typically by lowering the activation energy. You can typically identify an enzyme because it ends with the suffix ase. So we already talked about lactase, for instance, which breaks down lactose. And we did say it lowers activation energy. It acts as a biological catalyst, but there's one other criteria to an enzyme. What is the other part of the definition of an enzyme? It speeds up a chemical reaction. It lowers an activation energy. So when I add oxygen to a flame, that flame gets bigger. Is oxygen a catalyst?
No,
No, why not?
because it gets used.
Bingo. The
Mhm.
key to an enzyme, the key to a catalyst is it is not used up in the chemical reaction. In fact, part of its definition is it is unchanged by the chemical reaction. The advantage of this is it can be used many times. In fact, some of the enzymes that we have in our body are capable of doing thousands of chemical reactions in a second. Incredibly, incredibly rapid processes that can take place. All right. Enzymes are typically highly specific. They are, and I'll just draw a simple one here. Typically, they are globular in shape, but what's special about them is they have a very specific binding site, or what is known as an active site. And that binding site or active site is specific for just a specific structure. So like we said, lactase, its binding site is specific that only a lactose molecule can fit in it, right? And hydrases, like we talked about, are specific for carbohydrates and so on. Lipases break down lipids and so on and so forth. So typically they're specific to just one molecule, just one chemical reaction. And because their shape is so precise, they are very sensitive to temperature and pH. We talked about that salivary amylase, where when you swallow it and it goes into the stomach, it changes shape and because of the change in pH, and it is no longer effective. But there are other enzymes that do work at the pH of 2 inside of your stomach. So again, each one has its own optimal temperature and optimal pH. I really like this illustration from your textbook. I think they do a nice job of kind of showing this. Notice we have a globular protein. This one happens to be to facilitate peptide bonds with amino acids. So notice two individual amino acids come together. The enzyme facilitates the chemical reaction. Our peptide bond is formed, notice with dehydration synthesis so that water is released. And our now dipeptide is released and our enzyme is the exact same as it was before it left. This looks really nice. And the only thing I don't like about it is it makes the enzyme seem very passive in the process. This illustration isn't from your textbook, but I think it does an amazing job of really showing how many enzymes work. Notice again, we have a globular protein with, and I'll use pink since they use pink, a specific binding or active site where our molecules can come and bind. And notice when our molecules come and bind, the enzyme undergoes a conformational change. Again, these are one of those things that when you call grandma, you can say, hey, grandma, guess what? When an enzyme binds to a molecule, that enzyme undergoes a conformational change. And she'll be very impressed and she'll send you $20 in the mail. Can someone explain to me what that means? What does it mean to undergo a conformational change? No, it isn't that it can't be undone, although that's a good guess.
Make
Changes
sure
shape.
that
Yeah, exactly. All it means is that the molecule changes shape. And typically that change in shape does not involve ATP. So it's not actively using energy to change shape. It's using the energy of the molecule. It doesn't use ATP, but it's just a fancy way of saying it changes its shape. And notice that's exactly what happens. It changes its shape, and as it changes its shape, it folds up on itself. As it folds up on itself, it brings together the two molecules, allowing the chemical reaction to take place so that a new molecule is formed as a result. But notice once that chemical reaction takes place, our enzyme unwinds, and notice it is right back to where it was at the beginning of the process. Our enzyme is unchanged by this reaction and can do this hundreds or thousands or millions of times. So they can be very dynamic. They can be very active in the process. The key is that they're not changed by the process. All right. Questions on that?
Nope.
All right, excellent. That leaves us with our last macromolecule. Our last macromolecule are nucleic acids. Nucleic acids are made up of monomers, like all of our macromolecules are. And in this case, the monomer of a nucleic acid is a nucleotide. Let's talk about what a nucleotide is. You can see the picture of one here, but let's go ahead and draw it. So we're talking about our nucleic acids. Let's do that. That. All right, they're formed by nucleotides, and a nucleotide has three components. The first of those is a 5-carbon sugar. So again, we have carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. So we have a 5-carbon sugar. And anybody know how many different types of 5-carbon sugars can be found here? How
like
many?
altogether, one.
No, two, actually two. There are two possible. What are the two possible types of sugars that can be found here? Anybody know?
Ribose.
And?
Ribose.
Ribose and deoxyribose.
Deoxyribose.
Yeah. Excellent. So one of two possible types. It's either going to be ribose or deoxyribose. The second component to a nucleotide is a phosphate. Again, you don't have to worry too much about the chemical composition of this, but what you do need to know about a phosphate is that it is a very negative molecule. So this functional group is very, very negative. So we have this very negative. Right. And then the third component is a nitrogen base. Again, like proteins, nucleic acids are made from carbon, hydrogen, oxygen, and nitrogen, just like proteins. So the third component is some big nitrogen ring-based structure. And how many different types? How many different types of nitrogen bases can we have?
5.
5, excellent. Let's start easy. Just give me the letters associated with these possible bases. What are the 5 bases? Just give me a letter associated with one of these bases.
R.
No, not R.
G,
A is one. What else?
G,
G. U. Excellent. 2 more.
T.
T. And there you go. C. Excellent. Right. 5 possible letters. Now we can figure these out. These are nitrogen bases called adenine, guanine, uracil, thymine, and cytosine. Oops. Yep. So one of 5 possible bases. So you take one of our 2 sugars, either a ribose or a deoxyribose. You put it together with one of these 5 bases and throw a phosphate on there, and you have a nucleotide. Nucleotides are used to make our nucleic acids. And basically what happens is that, let's do it this way. The sugar and the phosphate form basically a backbone. So basically what we have is a phosphate in a sugar that connects to a phosphate in a sugar, which connects to a phosphate in a sugar, which connects to a phosphate and a sugar, forming the backbone of this structure. And then coming off of this is going to be the nitrogen bases. So we've got a base here and a base here and a base here. So we're going to have a line of A's and C's and G's and so on. And that is a nucleic acid. Now, as it turns out, not surprisingly, with 2 different sugars, there are 2 main types of nucleic acids. What are they?
DNA and RNA.
Excellent, which is absolutely 100% correct, except for the fact that in this class spelling matters. And because spelling matters, we're not going to get away with abbreviations. So on the exam, if you're writing out an essay, for instance, you can write it out once and then abbreviate it after that. But if I just asked you to identify the 2 types, we would need to spell it out. So what does DNA actually stand for?
deoxyribonucleic acid.
Excellent. And what does RNA stand for?
Ribose nucleic acid.
Ribonucleic acid, yeah. Excellent. Perfect. Now we'll learn obviously the ribose is used for the RNA, the deoxyribose is used for the DNA. We'll talk more about the rules of which bases are used with which and all of that as we get into protein synthesis and mitosis and all of those things. But for simplicity right here in basic terms, what are the functions? What do we use DNA for?
What makes you you? Creating.
Your gene?
Yeah, absolutely. Okay, so these form genes. And what do genes do? I like that. Extract protein's not a bad, but really they're the instructions. They're the permanent instructions to make proteins. And you guys are absolutely right. Proteins are what make us what we are. Everything about you. Your hair color, your eye color, whether you're right-handed or left-handed, your blood type, your predisposition to heart disease. All of those things are determined by proteins and these genes that give us the instructions of how to make those proteins. That makes it a pretty darn important thing. So important, in fact, that what do we do with this DNA? Where is it kept inside the cell?
In the nucleus.
Yeah, it's going to be locked up in the nucleus. I know we haven't talked about the anatomy of a cell yet, but hopefully most of us know what a nucleus is. So it's locked up there tight, held under lock and key. So when it comes time to make protein, does somebody in the cell come up with a library card to be able to check out the little piece of DNA that it needs to make the protein? What do you think? Think that's how it works? Does your cell have library cards?
No.
No, exactly. So instead, what happens is we make a temporary copy, temporary and portable, let's say, of the genetic information that can be used to make the proteins that we need. So DNA is the permanent instruction manual held under lock and key, and the RNA are little temporary portable versions of that information that can be used to make the proteins that we need and then thrown away afterwards. All right. Makes this vitally, vitally important. Here we see again that pretty picture, phosphates group, sugar, nitrogen base. We'll talk about purines and pyrimidines and what those mean later. We talked about that. And all of the important things that go along with that. So again, this is the vitally important function of our nucleic acids. Questions on that?
Nope.
Excellent. All right. There is one other vitally, many of you probably knew about DNA and RNA, and many of you knew about this last thing as well, but you may not have thought of it in these terms before. So let's go back to our fun little drawing here. Let's go ahead and erase this and 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 that and that and this and all of these. And come back to here. This, as we talked about, is a nucleotide. And as we talked about, a nucleotide is going to use one of these two sugars. And for argument's sake, let's make this sugar a ribose. So we're going to specifically use the ribose sugar. And of our 5 bases here, we're going to specifically use an adenine. So what I have here is a single nucleotide with an adenine nitrogen base with a ribose sugar and that phosphate. And again, the one thing we know about this phosphate, it is very, very negative. So let's decide that I want to do something kooky. I want to add a second phosphate to this nucleotide. Now, as we know, phosphates are very, very negative. So is it going to be easy to put two negative things together?
No.
No. I can form a bond between the two of them, but to do that, I'm going to have to use a lot of energy. And so this is going to be a high energy bond. That should make sense. But then I want to do something really quirky. I want to add a third phosphate to the party. Now, with two phosphates here, I have something that is really, really negative. And is it going to be easy to throw a third negative thing on here? These are the easy questions, folks. No, absolutely not. So I am going to have to use, and again, to use technical terms, lots and lots of energy to make the bond. And so this is going to be a very high energy bond. And after I've done all this work, what do I have as a result of all of my hard work? Fun drawing, pretty picture. There we go, absolutely. As an end result, I have an adenosine. Adenosine is the ribose sugar with the adenine nitrogen base on it, and 3 phosphates. And after I've written that out once on an exam, what could I possibly abbreviate adenosine triphosphate as?
ATP.
ATP.
ATP. And remember, as we talked about, ATP is the energy molecule of our cell. This is what our cell uses to do work, because that's exactly what happens. What we are going to do is split the ATP. When we split the ATP, basically what we do is we break the bond between the phosphate and the rest of it. And so when we split the ATP as a result of that, we release a tremendous amount of energy. And that energy can be used to do work, right? Now, when we split it, of course, we've ripped off a phosphate. So now we have that negative phosphate floating around by itself. And what else are we left with after this process as well? Once we've ripped that phosphate, what is the rest of this molecule called?
Adenosine diphosphate.
There you go. Which, after you've written out once on an exam, you can abbreviate ADP. But remember, this bond here between the first and second is actually a high energy bond, not as high as the previous one. So notice we could also, if we really wanted to, we could split the ADP. If we split the ADP, as a result of that, we would release some energy, a fair amount of energy. Obviously, whoops, we ripped off a phosphate, so there would be a phosphate there. And what would we have remaining as a result of this second split?
Adenosine monophosphate.
Which after you've written out, whoops, once, you could abbreviate AMP. Exactly. Everybody here knows what ATP is, but I don't think that most people coming into this realize that it's actually a nucleotide. Aside from forming our DNA, aside from forming our genes, aside from helping us to make proteins, our nucleic acids, or specifically this nucleotide, is our major energy molecule of the body. And again, I've done it here on the pretty picture, but let's take a look at the picture from your textbook. Again, here's that adenine nitrogen base. We can see the nitrogen rings that are forming it. Here's my 5-carbon ribose sugar. All right, so this is our adenosine. Notice with 1 phosphate, it's adenosine monophosphate. With 2, adenosine diphosphate. And with 3, adenosine triphosphate. And notice both of these are high energy molecules. But remember also that it is this third one that has the highest level of energy. So when we break that first one, we split that ATP, we rip that phosphate off that ATP. We get a massive amount of energy and ADP as a result. All right. Questions on that? All right, excellent. That is everything we need to know about chemistry. So our goal for today has been accomplished. Finished a little bit early, which is nice. So I'll be happy to field any questions on anything we've covered for the first 2 days or anything procedural that you have any questions about. I guess I should have asked this question at the beginning of class, so looking at the numbers. Is there anybody who's here today who wasn't here yesterday? If you're afraid to speak out loud, you can send me a private message on the chat. I don't think there is anybody who was, but hopefully that's not. But if you have, then please let me know. Everybody here, was there anybody who did not take the quiz, the attendance quiz? Okay, if everybody took that, again, I don't want to have to drop somebody who's not here because they forgot to take that. So again, if you need to do that, do that. Yeah, I can go back to the previous slide. Let's do that. There you go. All right, excellent. All right. Well, that is all the new material that I wanted to cover for today. I know we're finishing a little bit early, but things are going smoothly. So like I said, I will happily answer any questions that you have, procedural or otherwise. The one before this.
Do you think you could talk about kind of like contextually how we'll continue to use this information in the rest of the class?
So yes, obviously, well, so ATP is a perfect example. That is something that we are going to talk about the use of that for the function of a lot of the different organelles in our body or channels or transporters across the plasma membrane. When we talk about the cell, we're going to talk about the plasma membrane of the cell and its function. And so understanding the components that make it up are going to be important. When we talk about muscles, understanding that they store glycogen in them gives them the energy to produce ATP. So yeah, all of these things are starting to build the basic building blocks of how we're going to now make a cell. Then once we understand how to make a cell and how a cell functions, we can make tissues. And then once we start making tissues, we can put those tissues together to make organs. Oh, the drawing. Okay, I understand now. I'm sorry. So yeah, again, these are not things that I'm just randomly picking for us to go through. These are the things that we're going to be using to build upon. So this is the basis of what we're going to need moving forward from here. All right, thank you. I will make sure you don't get dropped then for that. Write this down. Anybody else not take the attendance quiz? Excellent. All right. Thank you for letting me know that. Excellent. All right. So
I have a question.
yes.
I know you said attendance quiz was just the first day and the second day. So does that mean we're having daily quizzes tomorrow or Thursday?
So as I mentioned, some daily quizzes are going to be announced and some will not. However, the fact that we have had, as far as I'm concerned now, attendance is closed. I don't have any new people who anybody who's on that question. I think everybody who had prereqs, actually, that's a good question. Let me check that real quickly. I think I have the prereqs for everybody who was here. Yes. So again, prerequisites isn't an issue. Everybody who was on the wait list was given an ad slip, except for one person who didn't contact me by email afterwards. But it is possible that I scared that individual off because they are not here now. So yeah, so everybody, I believe everybody who wanted to be in the class and has been here the past 2 days is now enrolled in the class. So I believe that that is indeed the case. So as far as I'm concerned, we are done with attendance. This is the class that we are going to have. But you're absolutely correct. Any day at the beginning of class or any day at the end of class, like right now when we finished early, we could have a daily quiz. So it is important to be here at the beginning of class. It is important to be here at the end of the lecture so that you are ready and available if those things are going to take place. And again, while most of them are not going to be announced, is it a safe guess? If I was the smart, sophisticated students that all of you are, would I think that the first day that we didn't have to take an attendance quiz would be a perfect time to have our first daily quiz, especially coming back after a day off? So when we come back like on a Thursday or we come back on a Monday, do those days tend to, when you've had a weekend or a day off to study these things, are those usually a good time to have a quiz? I think that that'd probably be a fair assumption to make. Yes and no. The quizzes, so there are two ways that I could be quizzing you on information. Some could be on the previous information that we've covered, and some could be on the information we're going to be covering for that day. Now, if the question is about a previous question from information we've covered already, then that would be more specific pieces of information. Right? I want more specific information. If it's about something we're going to be covering, then it'll typically be a more general type of question, right? So for instance, after today, you should know, what the quaternary level of the structural organization of a protein is, or that ATP is made up of a nucleic acid, right? Before today's lecture, you probably didn't know those things. So those are things that I could quiz you on tomorrow. Tomorrow, when we talk about the cell, I think a question that, like where is the DNA stored in the cell, or what is the, what produces the energy of the cell? I think most people kind of know the answer to those types of questions. Obviously, the nucleus. What is the powerhouse of the cell? Where is ATP produced in a cell?
Mitochondria.
Yeah, in the mitochondria, right? So those are more general pieces of information that people should know. Knowing that a mitochondria has a double membrane and the inner folds of the inner membrane, the cristae, is specific information that I wouldn't ask, but general information you should come prepared for these quizzes, at least having a basic understanding, or at least having looked at the outline slides to see what we're going to be talking about that next day. No, these daily quizzes are 5 points, 5 minutes. It would take you more time to set up the Proctorio and scan the room and do all that than it should take you to take the quiz. So the daily quizzes will not be proctored using Proctorio. It'd be a waste of time. So no, it's just a quick 5-point encouragement, free points for coming to class and coming to class prepared.
I had a question about ATP.
Yeah.
So I was just curious, what makes the second peptide bond between the second and third phosphate groups have more energy than the first peptide bond between the first and second phosphate group?
Yeah, it's all about the negative charge. Think of it in terms of magnets. When you have two magnets that don't like each other, right, it takes force to push them and hold them together, right? And the stronger the magnets, the more force you have to use. So when you just have one negative thing and you're trying to add a second to it, that's hard to do. But when you have two negative things that you're trying now to add a third to, it takes a lot more energy to add that third negative thing to something that is already really, really negative. So it just, because that's more negative than it was before, it now takes more energy to put a third thing onto it. Does that make sense?
Yeah.
Okay. Excellent.
So for the practice exam on Friday, is that going to be different than like the other exams that are on the schedule, and that are we still coming to class on that day?
Oh, yes. Great question. Yes. So absolutely, you're coming to class on that day. What we are going to, the practice exam, this is a great question. The practice exam is, I think, 20 questions. So and I think you'll have like 20 minutes to take it or something along those lines. You will use the proctoral protocols for this, but it is not graded. In fact, I'm not even going to look at it. The point of this is something for you to do to experience what an actual lab exam will be like. Excuse me. Now, this practice lab exam uses questions that have been on previous exams, and some of these questions might actually be in your test bank for the real exam. But again, that's one of the other things about these exams. One of the things you have to remember with this format is that, oh, and that's the other thing, for the practice exam, all of you are getting the same questions. So we're going to take it after lecture. So after lecture, we're going to take a break. You're going to come back from break. You're going to take it. And then after you take it, we're going to get together and meet and discuss it. For the practice exam, you're all getting the same 20 questions. I've purposely picked these questions for specific reasons. And after you've taken it, we will go through the exam together as a group, talk about why I picked them, what the answers are, and what you should learn from that particular question to help you in the real exam. When it gets to the real exam, this first exam, I think, is going to have somewhere around 70 or 75 questions on it. The format will basically be the same. And so that's the point of this, is to see the format. But your questions are drawn from a test bank. So on a real exam, and this is true for both the lecture and the lab exam, everybody's getting different questions. Everybody's getting different questions. And even if you have the same questions, they're going to be in a different order. So, so for instance, the cells, there may be a block of, 40 questions and it picks 5. For mitosis, there may be a block of 40 questions and it picks 5. And so everybody's going to get 5 questions on mitosis and 5 questions on cells. And again, I'm just randomly throwing out these numbers. Nothing, I don't know that that's true or not, but you get the right idea. But those questions will be different. So again, everybody's getting a different test. And again, there's some inherent, I don't even know what the right term is. The goal is, since obviously there's randomness to that. So some people might get slightly harder questions. Some people might get slightly easier questions. And unfortunately, that's going to happen. Not everybody's test is going to be equally easy or equally hard. However, the hope is that over the semester, right, some of your tests will be a little harder, some of your tests will be a little bit easier, and it'll all even out at the end. Right? But that's just the nature of the randomness of this. It's like flipping a coin, right? If you flip a coin 10 times, you should get 5 heads and 5 tails. If you flip a coin 10 times, are you always going to get 5 heads and 5 tails? No, but you're also not likely to get 10 tails either. So hopefully all of your tests won't be slightly harder than everybody else's. Hopefully some may be slightly harder, some might be slightly easier, and it'll all even out in the end. All right. And obviously we'll talk about this more when we're doing that on Friday as well. But we have 3 whole days before we have to worry about that. Millions and millions of time.
I was trying to see on the syllabus where it says what's included, like what chapters for the practice lab exam. I know it's not graded, but just to know.
It's going to be on everything we'll have talked about. In fact, up to, I don't think it includes Friday's lecture. I think it's just Monday through Thursday's lectures is what's going to be on that practice exam. I don't think there's anything from Fridays, but there may be 1 or 2. I don't remember. Again, it's not graded for content. So even if you haven't had a chance to study yet and it's just something on that day, then it shouldn't be that big of a deal. But if it is, I think it's only 1 or 2 out of the 20. I think it might just be, I don't think there's anything from Friday's lecture on it. So I think it's going to solely just be the first 3 days, I think. Yeah. So again, it should be a good indicator of how you're doing studying and preparing for the exam. So you'll get to see how I'm going to ask questions, what I'm looking for on these questions, what the right answers are going to be. And it's a good gauge to see how you're studying. But yeah, we're going to take it to the lab. We're not taking it at the beginning of the class. We're taking it during the middle of the class after we do the lecture. We'll do the lecture first, then we'll talk about the lab. All right. Yeah. Any other questions on any other information?
Yeah, I had another question.
Yeah.
Is there going to be a meeting tomorrow with the assistant instructor?
So yes, the open lab does begin tomorrow. So in fact, Jeff just sent me an email about that. A couple days ago. All right, let's see what he said here. So 10 hours on Wednesday, starting on the 9th, which is tomorrow, from 10:30 a.m. to 8:30 p.m. Is that what I have on the schedule? That doesn't sound right. Pages.
It's an all-day thing.
Oh yeah, 10:38 to, yep, and exactly. And it's the same link, so that's the same as well. So that's correct. Okay, so here's what he's written. I'm able to track attendance using the normal online attendance program, but I have to log them in as they arrive. The first time in, they will have to give me their student ID via private chat message. After that, I'm able to look it up. They also need to tell me when they're leaving so I can log them out, so that they will get credit for their full attended hours. If you log in and then leave, I think he defaults students to 15 minutes. So make sure you get credit for going by telling him when you show up and also letting him know when you leave. As I said, tracking is both necessary for our funding justification and also so that you get the credit for coming to the open lab. I'm using 2 cameras with a whiteboard set up for BIOL430. I have skin, cells, bones, muscle tissue models, skulls, nasal cavity flapboard, individual bones, half a head, large head, yammer, bunch of stuff that he's got. And then even more stuff for 431 because it's open for both semesters of this. Then he's got histology, he's got all sorts of things. So he is set up and ready to go and it will start tomorrow. So yes. All right. What's next? Anything else? All righty. Well, then I would tell you to enjoy your day off, but I would not mean it. Study hard tomorrow, study hard today. Again, you got tomorrow off, so take a good 15, 20-minute break, right? Cry yourself a little bit in the corner, and then I want you diving right into this material and making sure that you've mastered it and you're ready to go. When we now move up to our second level of the hierarchy, and we will start cells on Thursday. All right, any questions? All right, excellent. You guys have an excellent day, and I will see you guys on Thursday. Remember also, if you haven't done so already, remember the 5 for 5 appointments are available. I will be doing those today. I think there are a couple spots still open. So if you still need that 5 for 5, I believe, here I can confirm that. I think there are a couple spots still open. Nope, I lied. They're all taken. So if you need an appointment, email me and we will make those arrangements because it looks like all the other appointments which start at 1 are taken. So you guys have a good day off and I will see you guys on Thursday. All right, bye.